good afternoon to everyone, and welcome to the 2022 SEI Research Review. I'm Paul Nielsen, the Director and CEO of the Software Engineering Institute. It's been my honor to lead the women and men of SEI for the past 18 years now, as they work to improve the state of software engineering, cybersecurity, and AI engineering. It's a big task. During this time, the importance of software engineering has continued to grow. Software-defined systems connect us, bring us information and entertainment. They feed us, take care of our health, are critical to the supply chain, and are vital for defense and government. The challenges of cybersecurity have also grown throughout this time, whether defending against peer competitors, social engineering, ransomware, or even insider threats that we all have to worry about. And the advent of AI and ML, machine learning, have presented new opportunities and challenges to this increasingly complex and connected world. So in the middle of all this, the women and men of the Software Engineering Institute continue to work to improve the nation's capabilities, and importantly, to try to forecast the needs of the future, because we can't just solve today's problems today. We have to think about the problems of tomorrow. Now, I'm excited to bring you this year's research review. I get excited about this every year because I love scientists and engineers. I love science and engineering. And to me, this is one of the highlights of that, to see the new work that's being done and the enthusiasm of the people that are doing that work. I hope, like me, that you enjoy it, that you learn from it, and that it spurs new collaborations for all of us as we move into the future, because this is really a business that requires collaboration. Tom, I think it's time for you now. Thanks so much, everyone.
Thank you so much, Paul. Look, I want to reiterate as well. Thank you all for joining us this afternoon, this morning, this evening, wherever you happen to be in the world. I am Tom Longstaff. I'm the Chief Technology Officer here at the Software Engineering Institute. And it is my pleasure to host the annual research review, where we highlight a selection of our best open projects that have contributions not only for our PIs, but from other collaborators and people throughout the academic and government world that's out there. We have basically called this particular research review Forging the Path with Fundamental Science and Engineering. Why Forging the Path? Because we believe, especially coming out of the last 2.5 years of sort of the disruptions that we've had through COVID and through various kinds of working in different locations, that we're now basically all coming together to follow a path to a better way of working together and a better way of doing the research that we're doing. So we are essentially forging a path along a new road that's getting us to even better research results than we've ever achieved in the past. These research results are going to be brought to you by a variety of our PIs throughout the next 3 days. So we are doing this basically as 3 half days. East Coast time, it's noon to 4. We are going to be constructing or presenting a lot of the individual research projects that we've published on, and some that we just have recent results. So you'll hear some things at this particular research review that you have not heard before. This follows an execution strategy that you can see on the screen now, where essentially we take the technical objectives and the portfolio that we have with information from leadership and expertise throughout the world. And then we have a model where we study problems to publish papers, we make solutions and prototypes, we transition these into a variety of US Defense Department and government and industry. And then finally, after usually several years of effort, when there is a large amount of momentum behind each one of these efforts, we transfer them out so that we can make room for new work. As Paul just said a few minutes ago, we've recently added AI/ML as a big part of our portfolio here at the SEI. And, you know, on the order of 2 decades ago, we really got into cybersecurity as sort of a major way that we were working, I guess 3 decades ago now. uh, into cybersecurity. So we are always looking for what is the place that we can do applied research where we take the latest results that come from academia and from industry and really try to create a transitionable series of capabilities that we can really put out there to make a difference, both for us in the US and the Department of Defense and throughout the world, to really increase the level of software capabilities, cybersecurity, and AI ML throughout basically the world in terms of where that happens. The way that this works, though, is not in isolation. The study make and transition elements, the way that we forge that path, isn't as straightforward as you might think, because our study always leads to prototyping, which leads to some transition back into pilots and technical exchanges and sharing needs and engagement and policy and data. So all of these wrap together. So as we forge the path, they're not three independent paths. Whether those paths would be our individual divisions here at the SEI, or whether they would be the make study, the make study and transition elements that I'm talking about, but they all weave together. And I have to say, they weave together with you as well. They weave together with our partners, with our collaborators, with the people out there in industry and academia and government that we work together with across AI software and cybersecurity. So one of the things I would ask is look for opportunities throughout the next 3 days. If you see something that really sparks your interest, immediately what you can do is go to the Discord server. So the Discord server, you should have received a link to as you've registered for this particular workshop. As you register, you get a link, and this is where you can do live discussions with our PIs and other people here at the Software Engineering Institute to learn how to engage more completely with us, more fully with us. But then after the fact, there are lots of ways to work with us throughout. And I would really encourage everybody to say, not just passively listen. Don't just passively take it in, but think about how this works together with your interests. How does this work with problems that you might have? How does this maybe help to solve things in an innovative way? And then work with us. Collaboration is really what makes all of our work more effective over time. So the way that we're going to work the next 3 days, we have a master of ceremonies for each day who's going to lead you through all of the individual presentations and panels that we're going to have. Today, we're going to start with John Lee, who is a technical director and the head of AI engineering. Tomorrow, we should have Chris Rush, who's a technical director in CERT from our monitoring and response work. And then on Wednesday, Bob Stoddard, who's an initiative lead in software engineering, measurement and analysis, will help guide us through the day. And bearing illness or other kinds of swaps we may have to do last minute, those are the faces that you will see helping guide you through and connect you to all the various pieces that are here. Before I turn this over to John Lee, I just want to begin by thanking everybody at the Software Engineering Institute who's been behind all of the work that you're going to see, whether it be the PIs and the researchers that are here, the graphics and broadcast personnel, the writers, the engineers, and the people in the back end doing the IT and support that are all making this possible and out there for you. This year, we are doing this virtually. We've done this through the COVID pandemic and have gotten great feedback that virtually is the best way to reach you. But I do ask that if you have additional feedback for us on how to make this event better, please reach out and let us know as you see it. So without further ado, I'm going to turn this over to John Lee, who's going to help introduce our first speaker. John, over to you.
Thank you, Tom. Hi, I'm John Lee, the technical director focusing on AI engineering. In my area, we focus on the identification, creation, and proliferation of leading processes, practices, and tools for AI to make AI human-centered, scalable, robust, and secure. It's my pleasure to introduce our keynote speaker for today, Dr. William Bill Stryline. Dr. William Bill Stryline is the Chief Technology Officer for the Chief Digital and AI Office for the DoD. He works to provide strategic awareness, direction, and leadership for enterprise-scale data, analytical, and AI capabilities. Before his role at the Chief Digital and AI Office, he joined the MIT Lincoln Laboratory in 1998, serving in the Biotechnology and Human Systems Division. He supported efforts in bioengineering, bioinformatics, and biodefense, working on AI and machine learning approaches to solve national biosecurity, health, and human performance challenges. And in addition, Bill was leading the Cyber Analytics and Decisions Group, investigating cybersecurity, passive network, and traffic analysis, streaming analytics, and computer vision. He's also done a ton of work for the community. He serves as the chair of the AI for Cybersecurity and Robust AI Systems Assurance academic workshops. He's a member of the IEEE and the AAAI. Here's Dr. Stryline speaking on accelerating AI adoption for DoD Decision Advantage.
Good afternoon. My name is Bill Stryline, and I'm the Chief Technology Officer in the Chief Digital and AI Office at the Office of the Secretary of Defense. I am pleased and honored to be here today to tell you about the CDAO, its stand-up, and initiatives and priorities aimed at accelerating the adoption of AI for the DoD. As we know, this is a competitive environment. Our adversaries also understand and can see the potential and promise of AI for national security and national defense. When we think about adoption of AI across the space of DoD concerns, it's important to keep this in context. I like to think about adoption in this way. Along the x-axis, I've enumerated the spaces of DoD concern, from enterprise through operations through warfighting. Along the y-axis, I've used some terms to describe to a lesser or greater degree the amount of adoption of AI across the DoD space. As indicated here, I've provided a notional frontier for where I think current AI adoption is across the space of DoD concerns. In general, AI is perhaps more commonly found in enterprise circumstances than in operations, and even less so in warfighting. And the question we must ask ourselves is, where do we want AI to be within the DoD? Do we want it to be all the way to the right, in the upper corner, where everything we do is enabled by AI? Or is it sufficient to understand where the adversary is and be a few steps ahead so that we can remain competitive? Movement of this frontier requires adoption that enables both greater capability automation and autonomy. The CDAO was established specifically to accelerate DoD's adoption of data, analytics, and AI to generate decision advantage. It was formed from the JAIC, the Joint AI Center, the Chief Digital Office, or Chief Data Office, Advana, a data analytics platform, and DDS, the Defense Digital Services, sort of a rebel force within the department. Key functions of the CDAO include leading and overseeing DoD strategic development and policy formulation with regard to data analytics and AI, breaking down barriers within DoD institutional processes to data and AI adoption, creating enabling digital infrastructure and services that support components' development and deployment of data analytics and AI, as well as digitally enabled solutions. For those capabilities which are proven, one of the key functions of CDAO is to selectively scale those for enterprise and joint use cases. And finally, surging in the case of rapid response to crises and emergent challenges is a key aspect of CDAO. Our 2022 lines of effort include policy, strategy, and governance, enterprise, infrastructure, and services, and enterprise and joint mission solutions. Returning to my simple rubric, if you will, or graphic depicting the amount of adoption across DoD space, I find it instructive to think about the barriers to adoption and how we can combat them. The first important barrier is inaccessible data. You can't have AI without data, and DoD data is in general difficult to access. It's not necessarily visible everywhere it needs to be. It isn't necessarily interoperable. Another significant barrier is the lack of AI trust and resistance across the spectrum. Challenges within the acquisition domain represent a significant barrier to the adoption of AI. Antiquated processes that don't keep up with the innovation pace of AI make it difficult to accept or adopt new AI capabilities. When capabilities do get developed, they're often siloed, fragmented, making it difficult to join them together or interoperate. And finally, the domain itself represents difficult technical challenges that must be addressed before AI can be adopted. CDAO possesses a number of capabilities meant to push back against these barriers and move the frontier of AI adoption up and to the right. The first is the development of policy and strategy that will unlock data, if you will, enable it to be visible and accessible and usable. Data standards or patterns ensure that it is interoperable and can be leveraged within contexts that are relevant. To combat the lack of AI trust and resistance, responsible AI toolkits can help components understand AI and ensure its readiness. Human-machine teaming best practices, as well as education, help to break down resistance to AI. Modern vehicles for agile acquisition can enable AI, data, and analytics to be readily accepted, adopted, and procured. Mechanisms that allow program managers to try out capabilities on relevant data and support this innovative scale. Enterprise capabilities promise to break down barriers of silos and fragmented capabilities so that everyone across the space can leverage a proven capability. And finally, to address the technical domain challenges that are so significant, leveraging data analytics and AI within an algorithmic warfare context will enable us to address these challenges and keep pace with our adversaries. Now that's a lot to do, so naturally CDAO has prioritized its activities, as listed here. The first among these is training, enabling stakeholders across the life cycle of capability deployment, development, deployment, and procurement need to be brought up to speed with the implications of AI, data, and analytics for their contributions. Making sure that capabilities that are developed are assured is another priority, and we have much work going on in AI assurance. And it's not only the performance of the capability that we want to assure, it's the robustness within environments in which change is happening or the adversary is attacking. I've mentioned data quality and its importance for producing robust AI. And we have a handy acronym to describe those characteristics we'd like to see in data. VALTUS, or visible, accessible, understandable, linked, trustworthy, interoperable, and secure, reflect these key aspects we'd like to see in data. As a North Star capability representing a modern DoD, Joint All-Domain Command and Control represents a key focus for activities within CDAO, and we support that through the development of experimentation, leave-behind capabilities, a data integration layer, and metrics to monitor progress. On the topic of metrics, we're also focused on enabling senior leaders within the department to monitor, track the progress of business units within the enterprise space. We have a significant focus on the combatant commands. Within the AI and Data Accelerator initiative, we are focusing on bringing modernization, data and analytics capabilities to them to enable them to transform their operations, built from joint capabilities. And finally, a key focus is in the area of AI ML ops services and platforms that will enable those across the DoD to rapidly develop, deploy, and monitor AI capabilities that are supporting their warfighting functions. I'd like to focus a little bit now on two particular priorities, ADA, and then I'll move and talk a little bit about a model or vision for the platforms. As I mentioned, ADA stands for the AI and Data Accelerator Initiative. It was an effort that was launched about a year ago in the summer of 2021 to address the urgent need of Joint Force commanders wishing to achieve decision advantage during competition, crisis, and conflict. The lack of interoperability between the siloed architectures they're dealing with is too complex for combatant commands to address by themselves. And so, under the direction of the Secretary of Defense, the Deputy Secretary of Defense, we began an initiative to continuously engage with the combatant commands to provide expert teams on site to discover use cases for rapid AI and capability development. Importantly, to leave behind these capabilities that will be validated through iterative processes, enabling integration and experimentation events. In support of ADA, CDAO leverages an agile model for capability delivery. Consisting of two concentric circles, the inner loop enables quick wins, while the outer loop supports longer-term development. Beginning with the mission engagement stage, an ADA team understands the mission needs by meeting directly with stakeholders at combatant commands. Through analysis and assessment of their mission needs, a decision is determined if the capability can be provided quickly through rapid prototyping or leveraging an existing solution. If not, processes are begun to engage longer-term development, perhaps with an outside vendor. In support of this agile model, the CDAO leverages several enabling services, such as strategy and policy, to ensure that data is available and accessible and other processes are not in the way. Acquisition models are available to enable rapid procurement of AI capabilities, which I'll talk about next. Responsible AI capabilities ensure that any AI that is developed and delivered is ethical and traceable and responsible within a mission context. AI education is provided to make sure that stakeholders across the mission lifecycle, the model lifecycle, understand the implications of AI data and analytics for their function. And finally, AI engineering principles govern activity, enabling that AI procurement is scalable, robust, and human-centered. Enterprise services are also available in support of the expert ADA teams. Data, models, and community spaces allow rapid interaction, integration, and collaboration to create capabilities, while ModSim and T&E, as well as computational resources, enable modernization and transformation towards digitization. The Agile model leverages enabling and enterprise services to deliver both quick win and long-term transformative capabilities. A couple of words about the acquisition models that accelerate the procurement and delivery of AI solutions. These solutions streamline and standardize AI procurement and enable agile delivery of AI capabilities to the warfighter. They ensure maximum participation from a broad network of academic and industry partners, and they enhance the partnership with U.S. industry. Some of the successes, as listed here on the right, include the Draft Data Readiness for AI Development, or DRADE, a T&E RFP as well, and the Trade with Other Transaction Authority, which enable program managers to address and make use of a large number of potential vendors. Responsible AI principles enable the adoption of AI across the enterprise in a responsible manner. It increases the effectiveness of our forces, empowers everyone to apply DoD AI ethics principles, and adheres to the department's core principles, the law of war, and the nation's democratic values. It transparently promotes security, peace, and stability to the benefit of our society. Some of the successes include a DSD memo on implementing RAI at DoD, a subcommittee on responsible AI, and integrating responsible AI educational content into the AI Workforce Initiative. As well, there are several responsible AI international partnerships in which the CDAO is a representative. Returning now to CDAO priorities, I'd like to talk about a vision for the AI MLOps platform. Rather than think about a platform that would support AI and ML development and deployment, I like to think about it as a holistic adoption platform, the goal of which is to bring AI to the complete DoD. These are some of the principles that I've outlined that will help us understand what we're going for. First, The adoption platform should enable DoD to leverage AI to modern mission functions from the boardroom to the battlefield. It should engender a digital ecosystem in which industry innovation is leveraged while DoD skill sets are enhanced. We want to make sure that competition drives capability delivery, both between vendors and suppliers, but also internally within vendors as different model architectures and solutions are tried out. The digital ecosystem will also embody DoD guidance, standards, and toolkits that enable and ensure robustness. And finally, across the digital ecosystem, federation will allow for solution diversity, enabling joint warfighting that is more robust. The adoption platform should offer enterprise services to reduce barrier to entry with a focus on mission. It should enable monitoring and management to drive enterprise adoption goals. I'd like now to articulate several layers that are part of this adoption platform that I think capture key aspects and together provide what we want in an adoption platform. First is the conceptual layer, which you can think of the initial step involved in engaging with a stakeholder to help them understand the value that AI, data, and analytics can provide to their mission. As depicted on the right, these circles in a Venn diagram depict the relationship between mission, data, and analytics to enable decision advantage. The first step is to identify mission-relevant decision or challenges. You collect and label relevant data with respect to that mission, decision, or challenge. Features are created from the data that support AI and analytics. And finally, AI and analytics operating on those features provide mission insight that the mission stakeholders can leverage to arrive at a decision in the center of the diagram. Within the space of DoD challenges, there are those that are known and unknown, and solutions that are known and unknown. As depicted here, in general, enterprise challenges and solutions are largely known. The process of bringing AI, data, and analytics involves automation, digitization, so that capabilities can be provided much more rapidly. But as we move out from the origin of this graph through operations and warfighting, challenges become less well-defined, perhaps even unknown, and solutions become less well-known. It is here where the challenges of providing AI become more difficult. I believe AI engineering can significantly help the DoD to develop AI capabilities, not only for those that address the known challenges with known solutions by providing standards, best practices to enable interoperation, but also for unknown challenges and unknown in the operations and warfighting. The next layer down in our adoption platform is the functional layer, in which the digital ecosystem is realized. As depicted here, it consists of a large MLOps loop, spanning the spaces of DoD, industry, and our trusted partners, such as FFRDCs, including SEI. The goal with this loop, this depiction, is to articulate the fact that a machine learning operations loop needs to be distributed to take full advantage of the digital ecosystem. Focusing DoD on the low layer, the bottom layer, of understanding mission, collecting mission data, and labeling it appropriately allows DoD to focus on what it knows best while its talent is upskilled. This data can then be provided in a sanitized way and appropriately to the innovation spaces at the top, where training data, appropriate labeled, is leveraged within a competitive model development environment to produce best-of-breed or optimal models. These models are then brought back down through an assurance layer, leveraging responsible AI toolkits provided from trusted partners, guided through government standards and principles, finally through test and evaluation to make sure that the containerized assured models are most appropriate for a mission environment. The loop continues as operational real-time feedback is provided to help monitor the model and make sure that it stays within operational parameters. This distributed machine learning operations loop brings assured innovation to meet the mission need and addresses the current and ongoing challenges of DoD upskilling and modernization need to keep pace with our pacing adversaries. The next layer down depicts a little more depth about the services and architectural layer needed or potentially provided by CDAO to affect the digital ecosystem. Over the backdrop of multiple machine learning operations loops, which happen across the DoD, we can see a number of individual services represented. These services connect the mission data to the innovation space and enable capabilities that provide insights to be delivered to the mission. Certain services here focus on data, such as data labeling, ontology services to translate between different labels, mediation service to translate between different formats, resulting in mission data sets that are relevant for the development of capabilities. This data then can be provided through a data fabric that allows ready interoperation and visibility and accessibility. Feature stores and data stores ensure that others can access it, and responsible AI toolkits and a model repo continue to provide capabilities for delivery to the mission. It's important to point out the pipeline monitoring and management service, because we believe that this will enable monitoring of the adoption of AI across the DoD space and help direct activities. If we were to look at the model pipeline, the MLOps loop, which is spread across DoD, partner organizations, trusted partners, and also the innovation space, we can begin to imagine overlaying status of this pipeline. Imagine, if you will, a mission has begun its modernization process. Data has been collected. It is now captured in an authoritative data source and provided in a sanitized way to model development in the innovation space. However, maybe this isn't going quite as well as you expect. The training data might not enable you to arrive through competitive model development at an optimal solution. This results in model assurance not meeting needs, and the model that is delivered or not delivered does not provide the necessary capability to the mission space. With this notional example, I'm trying to indicate how metrics, instrumentation that is part of the MLOps loop, can help you monitor not only this individual loop, but also the pace and status of adoption across the DoD. Now imagine that we're tracking the status across all the MLOps loops across the DoD. While certainly a large task, it's important to think about this as potentially an aggregation of data from all of the MLOps loops, delivering capability to mission need. If we instrument the distributed MLOps loops pipeline at each step and aggregate the status across the joint capability areas, we're in a position to leverage insights to direct investment towards our adoption goals. Depicted along the bottom of this notional monitor here, we see the joint capability areas from voice integration, battle space awareness, through command and control, up through protection, and then finally corporate management support, otherwise known as enterprise solutions. The color coding indicates the relative advancement of transformation of machine learning within these different spaces and use cases. An MLOps loop that is green means notionally that the capability is up and running, the model is performing as appropriately, and when feedback comes back about failure in performance, it is rapidly corrected. The yellow might indicate that there's a hiccup in the process that needs to be directed, needs to be assessed and corrected, and red means there's a serious problem that needs to be corrected in the MLOps delivery of capability. Those that don't have color mean we haven't adopted AI there, we haven't begun the process and need to be addressed. And in this way, we can direct investment towards adoption across the DoD space. Bringing these steps together, we can see an overall vision for the adoption of AI tech stack, starting first with a conceptual layer for how AI can bring insights to the mission space, followed next by the functional layer, the goal of which is to affect a digital ecosystem. The service or architectural layer enumerates services that CAO can provide to support the instantiation of the adoption tech stack. And finally, the management portal allows monitoring and management of the adoption across DoD. Returning now to our original depiction of the adoption of AI data and analytics across the DoD space, we can imagine the impact of the activities I've described in the previous slides. With these activities, we can demonstrate how CDAO can accelerate AI adoption across the DoD. Beginning with infrastructure, as we federate and bring adoption to be more common, the frontier of AI adoption moves up and to the right, enabling us from a strategic perspective to be AI ready. This continues moving the frontier of AI adoption, where now we are federated with our use of AI from a strategic standpoint. As the infrastructure becomes integrated and adoption of AI becomes ubiquitous, the frontier continues to move up and to the right, enabling us to think from an integrated perspective within the strategic context. The frontier continues to move, and we are now AI capable. Our infrastructure becomes dynamic, ready to respond to threats in conflict, crisis, or competition. And now AI adoption has become integral to our warfighting. The frontier has moved up and to the right, and we remain competitive in our use of AI, eventually becoming dominant, achieving our North Star capability for joint warfighting. In this way, we can imagine a future in which CDAO has assisted the department in accelerating the adoption of AI, driving us towards strategic decision dominance. In summary, the U.S. is in a competitive race with pacing adversaries, but there are challenges in adopting AI at scale. The CDAO was formed specifically to address these challenges and accelerate adoption. The CDAO functions through strategic and tactical activities, addressing identified priorities within enterprise and enabling services. And the digital ecosystem vision helps CDAO achieve its vision of accelerating adoption for the DoD. We are on a path to achieving decision dominance. Thank you very much for your time, and I look forward to questions.
Bill, thanks for your talk on accelerating AI adoption for the DoD decision advantage. That was quite a broad picture, and we're excited to be a part of it and help you move that along. While we're waiting for some questions from the audience, I wanted to lead off and ask you an initial one to start things off. So what do you think, what do you see as the #1 challenge for the DoD in adopting AI, and what can be done to address it?
I think that's a great question. I enumerated a number of sort of impediments to adoption of AI, technical ones for sure, like inaccessible data, siloed capabilities, and those sorts of, and then the difficulty of the technical domain itself. A lot of challenges are there. But I actually think the #1 challenge relates to cultural acceptance of what it means to leverage AI. And what I mean by that is that AI is constantly evolving. It means being willing to accept new solutions to problems you may have encountered. And that requires a new way to sort of look at how the problems are solved, how missions are executed, how technology is procured. And I think that will sort of drive a fundamental sort of transformation of the whole procurement process overall to enable this innovation to be captured in a way. So in a way that's obviously beneficial. The days of set and forget are long gone. Monolithic programs, while they certainly do exist, don't match this sort of paradigm of technology innovation. So I think that cultural idea where the solution we have now can be iterated on and improved, I think is probably the biggest challenge. I think people are willing, but it takes a lot of work to do that, I think.
Yeah. It sounds like it's not just a technological thing. It's really going to be about everybody in the culture and the business.
Yes, exactly. Certainly, to be fair, there are certain huge technical challenges that remain there. But I think understanding the implications of this sort of technology are what we need to encounter and go up against to leverage it.
So here's a question that's near and dear to me as an FFRDC. What do you see as the role for trusted partners in your vision for the digital ecosystem?
Oh yeah, thank you for that. I see, in my distributed MLOps vision there that I was able, given the opportunity to describe, I see it's really about a really strong partnership between, the DoD being able to leverage what's going on in industry. Now, industry for sure is a partner because they're going to be developing this vision anyways, developing technology that can be leveraged against the missions. But there's a key role, an absolutely critical role for that trusted partner to help translate the needs of the DoD into something industry can understand, and to also help assure the capabilities that, in my simplified loop, come back in. And the trusted partners, and I'm thinking of FFRDCs and UARCs and other facilities like that, are in the best position, who understand sort of what it means to do government, to do government work under the government policies and restrictions, but at the same time have the technical knowledge, skill set, and the finger on the pulse of innovation to be able to join the two of them. And part of the trusted partner aspect is that they're impartial, and so they are able to then tell you like it is, and not be swayed, if you will, by anyone who has an agenda. And that's exactly what you want in that position.
Oh, cool. Thanks, Bill. And as we think about like what we're doing here, I also wonder what others are doing. What are your thoughts on the US's focus on responsible AI when our adversaries might not be similarly focused? How do you see that working?
Yeah, no, that's a great question, and something that I and my colleagues at CDAO think about a lot. The DoD was the first organization to put out principles of ethical AI use and responsible AI, and they are core to the type of AI that we leverage. I often think that when we talk about AI, we should only talk about responsible AI because that's the only type we'll do, if you will, the only type we'll leverage. Going up against adversaries, it's almost like a situation where we're playing against folks who don't play by the rules, right? That's one way to think about it. However, from a technical perspective, there have been several papers that show when you leverage things like adversarial training, things that bring into your training set perturbed versions of the data set as a protection against seeing that in the real world or doing operations, you actually get a more robust algorithm. And I think that's the way we should be looking at our AI, that it enforces guardrails, if you will. You may lose a little bit on performance, but what you gain in robustness when the environment changes, when the data drifts, can really help you out in the long run. The organization or the players, if you will, who don't use responsible AI may be only looking at that one aspect of performance, and may be then, blind to what we all know is it can happen with adversarial AI. Slight shifts in the data points that are being presented to the algorithm can result in a completely different answer. And so I do think it's extra work for sure, but I think it's absolutely critical. Back to our previous question, I think trusted partners can really help us with that as well, and helping us assure that the capabilities are robust to all sorts of changes is really what we're after.
Thanks, Bill. We're getting a bunch of questions in from the audience. Let me throw a couple of them at you. This one might be a little bit challenging, so you can kind of take a little bit of time to think about this one. How did the various ML ops loops incorporate considerations, adaptations, decision requirements necessary to deliver joint cognitive systems, so human-machine teams that can operate effectively under mission pressures when deployed?
That's a great question, and I don't go into that very much in the talk that we just listened to, but I do think that human-machine teaming is absolutely critical for effective use of AI. My initial thoughts on that are that I think it's responsibility throughout the distributed loop, not in any one particular section, if you will, layer of that view. But I think the largest, perhaps the largest responsibility, and at least initially, relies with the mission stakeholders. I think the mission stakeholders are in a position to understand what it means to bring AI in. I like to think about that in 3 layers or 3 stages. You can adopt AI, sort of a one-for-one replacement of an activity. There's adapting to AI. Maybe you decide to elide a couple of steps in your process or shift something, change the order. And then there's transformation. That's a big jump there, but at least those 3 indicate different levels of incorporation of AI. And throughout that process, you've got to think about human-machine teaming. What does it mean? In the first case, when you're adopting AI, I think you really are trying to be very specific about what it is that you want the AI to do. Maybe it's you want it to do OCR on handwritten forms. That's a specific thing, and you can probably have pretty good guardrails and understanding of what comes out of it. When you move to adapt, you're putting together 2 processes or 2 steps that might have been done by one human. And I think the science is still out. We're not quite sure how to do that in terms of understanding what the machine is doing for us. And then when you get to transformation, I think that's a wholesale rewriting of the mission. And so understanding how the human can interact with such a system relies upon developing metrics that help us understand what we really want from it. So there's a need for all partners in that distributed MLOps loop to consider that. I think, like I said, I think it begins with the DoD understanding it, and then through the conveyance of the data that can be used to build the models. I think as we learn more, we'll also convey sort of the constraints that are necessary to form a team.
Mm-hmm. Yeah. I mean, this human-machine teaming idea is something that's pretty fascinating for me. I think that there's a lot of development to do to figure out how human and AI teams will exist in the future. Maybe as a follow-up question to that, what do you think the benefits are to people or our mission partners or the folks in the field from adopting AI? Will AI make their lives better, or is it just another thing that they're going to have to learn to work with?
I believe it's going to make, well, I have to believe it's going to make everything better. I don't want it just to be something else to work with. I think, there's 2 things. It's coming no matter what, and we have to get ahead of it and understand what it means. I like to think about it, and I've heard others say this as well, is leveraging AI basically sort of enables all echelons of an organization to participate in the decision making. And that, I think, is the real win. It speeds up the decision cycle within an organization that might have used a hierarchy to send it all the way up to leadership and then come back down. Leveraging AI enables everyone to participate in that, to see for themselves the value in the predictions, the inferences that are coming, and then how that impacts it. And I think it's a real, I don't want to say force multiplier because that term's sometimes overused, but it does let you leverage all aspects of your organization. The more AI ready you are, and that's what I see as really the main benefit.
That's a good answer. Thanks, Bill. We have another question, which is kind of interesting, where we talk a lot about AI, and then here's a question that says, well, is sometimes AI not the right answer? So one question is, in the rush to AI, ML across the DoD, is the CDAO also helping elements understand when AI is not the answer, but there are better ways with existing capabilities?
Absolutely. In that diagram, I forget which slide it is I showed, but in the space of problems the DoD encounters, there are those problems for which we understand the challenge, the technical challenge, in which we may have solutions. And it may be there's no reason to leverage AI for that, unless you can optimize or something like that, and then you can do it. In the case where there isn't even an understanding, the situation is complex, so complex, or maybe even chaotic, you need something that's going to help you make sense of the data. Assuming you're able to assure that capability and get trust for it, your human machine team can trust it, you kind of have no choice. That's one of the things about it. I think we, in CDAO, we want to go after bringing, enterprise capabilities to the department that enable everyone to be able to make that decision as well. If the ultimate goal is, being competitive with their adversaries, and it doesn't require an AI, then absolutely we're all for it. But find that, or I believe it won't be possible to do that without at least some digital transformation, which is a first, as we were discussing earlier, and absolutely necessary step before you're able to put AI on top of it.
Thanks, Bill. A follow-up question that's related is related to your question about bringing these capabilities to the department is, how does the CDO collaborate with, say, the Air Force and the Navy for providing these types of services?
Right, and that's a great question. I appreciate the opportunity to talk about that a little bit. Since Craig Martell, our director, started 5 months ago, he's been really working hard to think about what it is the CAO can provide to move things forward, and we don't need yet another platform, if you will. Not that one isn't needed, but we don't want to jump headlong into building one. There are a lot of capabilities already out there. And so we're trying to think through, we're actually conducting a survey in a few weeks, reaching out to DoD and partners as well to understand what their pain points are with regard to AI ML. I've heard it said that, although there are a number of platforms across the services, at some point everybody hits a wall. And we want to help try to break that wall down, whatever that is. It may be data inaccessibility, it may be authority to operate, it may be connectivity, in a theater environment. So we believe that all of the platforms we have right now play an important role. And the key way to enable that is through a federated fabric, if you will. I like the word fabric because it suggests that we're knitting capabilities together, but it comes through standardized APIs, common vocabularies that are used to describe the data. Data itself doesn't have to be everywhere, but metadata around that data should be, so that you know what it is you're looking for. And the same thing can be true about models and computing capabilities. That's really, I think, how we're going to have a biggest impact, by federating capabilities.
Yeah, I saw that there was another question around models, and we were talking about there's this need to create a federated ability to share models across the DoD. I think we have time for just one question. I had a comment about your slide where you talk about unknown challenges and unknown solution. You mentioned that one of the biggest challenges is going to be unknown and unknowns, right? But how do you think about discovering challenges that you don't yet know about?
Yeah, that's a great question. That's the most difficult part of that of that graph is that it sort of mathematically has to be there. But I would say it comes through exploration. I think you don't what you don't know won't hurt you. I don't think that's true at all. I think we have to be active in finding challenges. And in fact, adversarial AI is an example of just such an activity where, perchance, by accident, I actually don't know the origin of the adversarial AI work, but maybe somebody thought that, hey, maybe if I just perturb this a little bit, I can get the results to flip. So somebody inventive thought of that idea, or putting something physical on a stop sign or something like that. So I think we have to be constantly exploring. We can't define the rules for how we're going to engage and leverage it. I know that this concept, I know a lot of people in the audience are familiar with, but this notion, Netflix uses a chaos monkey to just sort of wreak havoc within their network. And I think the same sort of thing is necessary here within the DoD. It's not a set and forget. We've got to have things going around, breaking down our systems, breaking down our inference engines. And in the operational environment, I think we have to do the same thing. I'm hoping that some of the AI can help us the same way we're using it through these large generative models to generate images for us. Maybe we can use something like that to generate unknown challenges and give us something to focus on. Thanks,
Bill. Thanks. Well, here at the SEI, we're very excited to play a role as a trusted advisor and be a part of this vision. The SEI and I would like to thank you first for the work that you do with the DoD, and then for moving AI forwards and your thoughts on accelerating AI adoption in the DoD. Well, we'll now be going to a break, and we'll be back at 1 p.m. for our first speaker of the day. Thank you. Thank you.
Hello, my name is Eric Heim, and I'm the principal investigator on a project titled Knowing When You Don't Know, AI Engineering in an Uncertain World. Robustness is a key consideration when engineering AI systems. Ensuring robustness, however, is a challenge due to the inherent uncertainty in DoD tactical environments in which AI systems are deployed. Motivated by this, our work focuses on quantifying, characterizing, and mitigating uncertainty in machine learning models, which are often at the center of AI systems. In this talk, I will discuss our work on using uncertainty measures for characterizing error. Here, we focus on object detection, where a model is tasked to identify objects of interest in imagery, a task with application to several ISR missions. I will discuss how modern object detection is commonly done, and then show how simple changes to and interpretations of these models can enable measures of uncertainty in their predictions. Our work builds on these interpretations to characterize failure of detectors while they are deployed. I will show some preliminary qualitative and quantitative results, highlighting cases where uncertainty measures are strong indicators of specific failures. Finally, I discuss where we are taking the work given some early results we've achieved. Thank you, and come see my talk.
Commanders and warfighters are demanding increasing analytic capability using the latest advances in machine learning at the tactical edge for decision advantage. This means squeezing more processing capability from systems subject to extreme size, weight, and power constraints, or SWaP. With an explosion in the variety of hardware becoming available in this space, too few engineers have the expertise to optimize the software for all of these platforms. I'm Scott McMillan, principal investigator on a project called Portable High Performance Inference at the Tactical Edge, or FIGHT for short. In partnership with Carnegie Mellon University's Electrical and Computer Engineering Department, our goal is to reduce the development time of highly optimized software for low-power hardware. Join the SEI Research Review to hear about how we have designed a library architecture that makes recent research advances in high-performance computing of machine learning operations digestible by the end user. The library is called Software for Machine Learning Libraries, or SMAL for short, and will be released as open source in the coming year. It exposes a standard programming interface for machine learning developers while defining a minimal number of low-level routines that need to be optimized for targeted hardware platforms. With its innovative design, a wide range of hardware platforms can be supported from low-power microcontrollers to small GPUs and beyond. By focusing on both usability and performance portability, the software developed in FIGHT can rapidly put increased computational power into the hands of the warfighter at the tactical edge.
Welcome back. I'm excited to kick off our research talks for today. In our first day of the research review, we'll be exploring ideas within the Forging the Path theme and continuing to look at accelerating delivery and adoption of AI. While there has been so much development over the last decade of AI, with the start of deep learning, GPU-based AI, large language models, and vision models, we still see that there's a lot of space left to go and a lot of things left to be done before AI becomes our AI reality. Today, we will hear talks on how to combat challenges around uncertainty in ML, enabling ML in some of the smallest devices in the edge, how mismatches in the organization create challenges for the success of ML, what to do with deepfakes, and using AI for AI cybersecurity defenses. We'll start the day with a talk by Dr. Eric Heim. Dr. Eric Heim is a senior machine learning research scientist at SEI's Emerging Technology Center. HIME's research focuses on practical issues of applying machine learning methods to real-world environments. Such issues include data scarcity, model robustness, learning from structured data, and enabling models to express reason about uncertainty in their predictions. HIME has applied his work to problems ranging from identifying man-made structures, from LiDAR measurements to estimating RF signal propagation effects from aerial imagery. Before arriving at the SEI, HIME was at the Air Force Research Laboratory, and he earned his PhD degree from the University of Pittsburgh. Let's hear Eric speak on uncertainty in machine learning.
Hello, my name is Eric HIME, and I'm a senior machine learning research scientist here at the AI division. I'm here to talk to you today about a project called Knowing When You Don't Know, Quantifying and Reasoning About Uncertainty in Machine Learning Models. First, I want to tell you a little bit about our team here. We have a number of awesome researchers and developers and engineers on the project, including 2 faculty members from the machine learning department, R.T. Singh and Zach Lipton. So I want to sort of give you sort of an illustrative example about what I mean when I talk about quantifying uncertainty. And note that this is one specific example we'll be carrying throughout this talk, but really there's a number of applications for which quantifying uncertainty is particularly useful. But consider this case here where you're trying to do some ISR tasks, where you're trying to identify, say, cars here in this scene from a ground level vehicle that has a camera on it, right? And so if you're trying to get some intelligence or do some reconnaissance in this area, what could be useful in this case is an object detector or a machine learning model that's able to detect objects in this scene. And so a common machine learning model, an object detector, that's able to do this task will output something that looks like this. And so it'll be a bounding box representing where the image is, where the object is, and the class of that object. In this case, it's a friendly truck. And in some case, this is useful to someone that's trying to reason about or actually take actions on what objects are in this scene here. But it's actually fairly limited. It doesn't tell you a lot about what's going on with the model or how much you should trust this particular prediction by the model. What's actually more useful, potentially, is some notion of confidence or uncertainty in the prediction. So, for instance, in this case, if the model says that this friendly truck is there and it's a friendly truck with 98% confidence, that is a different thing than situation than potentially saying that this is a friendly truck with 50% confidence. So certainly someone who's consuming the output of this model would treat those 2 situations differently. So this is why we say that accurate estimates of uncertainty can lead to better informed decision making. But that's not the only reason why you potentially want to quantify uncertainty in ML models. So consider this case, instead of actually showing the results of the ML model to a human, just the predictions themselves, maybe you want to actually use to put dots on a map. So you want to find where the objects are in some sort of larger context, say on this map here. And so in this example here, this green triangle is the camera or the robot that has a camera on it. And so what you may do is if this camera or this robot detects a friendly truck, it may, in the previous example without confidence, there's not much else you can do than, based off the model output, put it on the map right there. But if you have some notion of confidence or conversely uncertainty, you can make more informed decisions or reason more robustly about this particular instance. So for instance, if the confidence in this prediction is greater than 50%, you could pretty confidently put the dot on the map saying this is where the friendly truck is, and we know it's a friendly truck. If the confidence is less than 0.5, you may be less sure. So you may be confident, say, in the localization of this, where where this object is, but maybe not know enough about what the object is. In this case, you could potentially maneuver the robot to get a better look at this. And so in this particular case, you could get more confidence or a better prediction simply by monitoring the confidence that's coming out of your model. And so in this way, by allowing sort of higher level reasoning to take place based off of this confidence information, allows AI systems such as this one to be more robust to failures caused by unconfident predictions. And so just sort of to summarize a little bit about that, what we're saying here is that ML models that can accurately express their uncertainty can better inform end users, and in this way actually give them a better sense of trust in the AI system. Similarly, if you have built AI systems around this notion of confidence or uncertainty, you can do so more in a robust way. They can be evaluated, debugged, improved upon, and built around in a more robust way. And this is actually important for a lot of cases within the Department of Defense and intelligence community. In fact, the National Security Commission on Artificial Intelligence released a final report just recently where they actually cite this specifically for robust and trustworthy AI to be a concern for them. So our work here on this project is in evaluating, characterizing, articulating, and rectifying uncertainty in ML models for the purpose of more informative and robust AI systems. Specifically in this talk, we'll talk about a little bit of work within the project on using uncertainty as a mean to characterize errors. And so we're going to go back to this object detection case, like I talked about before, to show some of the work we did. And so to break this down a little bit, let's talk about what modern object detection looks like. Object detection really is two tasks done in tandem. First is that localization bit, where we're trying to define where in the image objects are. And the second one is the classification bit, what those objects are. And so practically what this looks like is this. So say we have this scene here from like a self-driving car data set. What happens is it's input into what's most commonly a neural network, a modern deep neural network. And output is the things that we showed before, these classes and the localizations. Now, more specifically, what happens in these models typically is of the following form. First, the images are input into what's known as a backbone network, which extracts relevant features from the image to do further processing. That's typically then fed into two different heads of the model, one being the classification head where classification is performed, and one is in the localization head where localization is performed. And the localization head usually outputs something like that looks like, for each object that it detects, 4 real valued numbers that correspond to coordinates in the image. And so in some cases, this can correspond to, say, the upper left and the bottom right coordinates of a bounding box surrounding the image. And so what this means intuitively is that the model thinks that all of the pixels contained in that bounding box include the image in question that you're trying to detect. Similarly, for each of those objects that are detected by the localization head, there's a classification component. And for this, there's a series of probabilities associated with every class that you can potentially classify in this domain. So one output could be something like this, where the class for car could receive, say, 0.9% probability or 90% confidence if you choose to interpret it that way. And so what's most commonly done is the prediction of this class or of this object for the class is the maximum value. In this case, it corresponds to car, so this bounding box is assigned the class car. So that's how modern object detectors work. But if we want to include uncertainty in these models, a little bit more introspection is required here. So first of all, what we're going to actually be talking about here is what's known as predictive uncertainty, and that's uncertainty output of the model. The outputs here being the bounding boxes in their classes. Digging a little bit deeper, really what the sources of uncertainty that can happen, that can lead to predictive uncertainty can be defined as epistemic or aleatoric. Epistemic means uncertainty in the parameters of the model, meaning that the model itself has not seen enough data to be confident in its predictions in that particular instance. And so this can actually be relieved by collecting more training data and training your model on them. Aleatoric, on the other hand, is uncertainty caused by inherent noise in the data. So this can be things like a sensor failure, like your camera failing, or adverse weather effects that occlude images or things like that. Note that this is type of uncertainty cannot be reduced by more training data. There simply isn't enough signal in the instances to do accurate predictions. So that's where uncertainty is caused for aleatoric wise. And so we're going to talk about uncertainty just in both the classification and localization components of an object detector. So the good news is for most modern object detectors, they speak the language of probability in terms of classification. Specifically, they output, like I talked about before, these probabilities which you can take a look at and reason about its uncertainty with just by looking at those. So what we're going to be using in the examples you'll see later is one interpretation of those probabilities by simply just looking at the maximum classification probability. Also, that relative to potentially other ones that are in that vector of probabilities. For localization, it's not as quite straightforward. So if you're just giving coordinates that correspond to the location of a bounding box, there's no obvious interpretation of that being of uncertainty for that particular output. So what do we do? There's a lot of different ways you can actually do this. What we did in this, what you're going to see later, is we used a technique called loss attenuation, which is from a paper in 2017. which actually, instead of outputting these bounding boxes, they output distributions over those bounding boxes, namely normal distributions over those bounding boxes. So instead of just saying the upper left and the bottom right-hand corner, or the center point, the length and the width of the bounding box, you actually have a mean and a variance associated with each of those 4 numbers. And so really what you can do then is using these probabilistic notions of distributions here, you can use them for classic ways of reasoning about uncertainty in normal distributions. So we use a particular form of normalized entropy for those distributions. So that's a lot of that established work. What did we want to do with this? So what we wanted to look at is, okay, so if these models are expressing these uncertainty measures, what can we do with that? What can we do? What happens when these models are uncertain? So I'm going to run through 2 examples here real quick from a model we built just to sort of get some intuition. And these are some preliminary results we've achieved through the early parts of the stage of the project. So what you're seeing here is an object detector we built on what's known as the Berkeley Deep Drive dataset, which is a self-driving car dataset. And they're trying to detect things like people and trucks and bikes and people on bikes and things like that. What you're seeing here in the blue bounding box is a detection that our object detector picked up. And notice directly behind him and sort of a little bit to the left here, you're actually seeing a person on a bike. And what you're going to see here is that on the right is those relative probabilities associated with each class. So right now, the model is very confident that this prediction is a person, which it should be because it is. What you're going to see here is the person on the bike actually go behind the person who's walking that's currently being detected. And that's going to cause a sense of an error actually in our model. What you're going to see, though, is if you just take a look at some of the probabilities that are being output by the model, that there's going to be a clear signal through the fluctuations of those probabilities when this is going to occur. So as we run this forward, we'll notice as the person crossed behind it right there, the rider class gets a lot of probability with that bounding box. And notice we're going to roll it back here. For that second right there, it actually made an incorrect prediction and thought that bounding box, which was a person, was a rider. But note that that specific event was highlighted by looking at the probabilities of output of our model and noticing a stark change. Here's another one that was for classification. We can also express uncertainty, like I said, in the localization. Here, this is some work we have with the project called or ATR MCAS project, which is this data was collected with some collaborators at the National Robotic Engineering Center, and they collected this over in one of their sites here locally. What they're trying to do is to detect this truck here, and what you're going to notice is we're going to have a heat map here that represents the localization uncertainty. And so when it's when the model is very certain, it's going to be a very tight bounding box, which a lot of the pixels are going to be red for very confident, and very few of the pixels are blue for unconfident. As it gets more uncertain, you're going to see less red and more cooler colors as displayed in our visualization here. And so as we run this forward here, again, very, very confident that the middle pixels there are indeed this truck, but you'll see a particular frame here in a couple seconds there, for which the model becomes uncertain, and then the next very frame, the model actually loses that object. And so what happened was that truck went behind that brush, became occluded to the point where the object detector could not accurately localize that object anymore, but that event was actually preceded by a significant drop in confidence in the localization. Again, in this case, by monitoring the uncertainty of the model, we were able to sort of detect that this event, this error was going to happen. And so the point here is that we've actually, sort of in a qualitative sense in a lot of our preliminary examples here, showed that increases in uncertainty or decreases in confidence seem to correspond to challenging detection events, such as the ones I showed there before. And so to get a more complete picture of what's happening here, we did some preliminary quantitative experiments as well. And so what we wanted to show is that on this Berkeley Deep Drive dataset, the self-driving car one, we were able to show the difference between correct predictions and incorrect predictions relative to the uncertainty estimates that are output by the model. So in this case, what we did here is on the test set, we actually plotted a histogram of all of the maximum probabilities that are output by the model by true positives, correct predictions by our model. And we notice here that most of the predictions for our true positives are on the high end, tend to be between 0.9 and 1.0. So very confident predictions when our model is correct. Conversely, what we found that for the false positives, most of the predictions tended to be low confidence. And so what the point here is that there's a very stark difference that you could potentially use these uncertainty estimates to sort of differentiate when the model is going to be correct or produce a true positive versus when it's going to be incorrect, a false positive. We did a similar experiment with the localization component of this model. And on the x-axis here, what you're seeing is our measure of uncertainty in the normalized entropy that we used. So here, higher is more uncertain. And on the y-axis here is intersection over union, which is a metric associated with quality of localization for object detectors. So here, higher is better. What you're seeing here is a high correlation between these two variables, a high negative correlation. Specifically, when the model is more uncertain, so lower entropy, there tends to be, more certain, which is low entropy, there tends to be better localization, high intersection over union. Conversely, when the model is more uncertain, so high entropy, the model tends to be have a lower localization quality, so lower intersection over union. And so this actually shows a little bit about not only in the qualitative sense does this seem to be happening in our model that there's events that are associated with these differences in uncertainty measures, but also overall, in sort of a more quantitative sense, these actually correspond to errors in either classification or localization. So let's bring this all together. So what we've witnessed here is both a qualitative result, preliminary result that said increase in detector uncertainty sort of corresponds to particular events, and quantitatively showed that increase in detector uncertainty corresponds to errors. So bringing these together, we want to use the context that's happening in these images and these uncertainty values to characterize potential errors. More specifically, we don't want to just predict when errors happen, but also characterize or describe the events that cause them. So what we can do things is like, predict when errors are going to happen with respect to occlusions, or when objects overlap, or when objects leave frame. But even if we didn't have that context, we can at least differentiate between localization errors and classification errors by measuring those two notions of uncertainty. Now, the practical benefit of this is this provides a lot more information to a person that is consuming the output of the model. So knowing that there's an error that's likely because an object is we can't localize the object, but we know what the object is, provides more information than saying we don't know there's going to be an error here. So characterizing the error allows people to make more informed decisions in this case. And also, if you build systems around this model, or around such a model that's able to express uncertainty in this way, potentially like mitigation strategies can be taken if you characterize the errors in specific ways. So in summary, uncertainty can be a key component to more robust and trustworthy machine learning models. And what we showed today was how uncertainty can be quantified in modern object detectors, some qualitative results showing events causing the detector to be uncertain, some preliminary quantitative results showing how uncertainty corresponds to error, and we outlined some of the directions of future work, which includes bringing this all together to actually characterize errors, not just detecting when they're going to happen. There's also a number of other sort of more technical ways to combine these things or to improve some of the results we showed. Like I mentioned, calibration can be used to make sure our uncertainty estimates are better or more reflect the actual empirical events that are happening. But also things like, hey, can we build models? Can we learn these notions of uncertainty without affecting the accuracy of our model? Can we do it in a data efficient way, meaning that we don't need a lot of additional data to get this sort of extra capability of predicting these errors? So this is just one part of the project. Last year at Research Review, I talked about some of our metrics and calibration work. That was accepted to a workshop at the International Conference in Learning Representations, a workshop in machine learning evaluation standards. We have some awesome work from our folks on campus, including some work from Zach Lipton's group about learning from limited sources of information. And also something I didn't talk about a lot about today, what is called is out-of-distribution detection or out-of-domain detection. And in this case, you're actually trying to detect when an instance is input to your model that your model couldn't reason about it because it's so different from everything it's seen before. For instance, if we're detecting people and cars and an airplane flew in, but our model has never seen an airplane before, simply being the model to be able to say, hey, I don't know what this thing is, maybe I need more information, is sort of an important task here in reasoning about uncertainty. Thank you.
Thanks, Eric. It's good to have you here to answer some questions about your research. I'd like to kick it off by asking you a question. What spurred this interest in understanding errors through the lens of uncertainty in object detection?
Yeah, there's I think first of all, thank you for having me give this talk, but I think a lot of the interest spurred from a lot of the people we spoke within the DoD and the intelligence community. They had this really simple question of, I don't know how to reason about when I build an ML model and I'm using it for deployment. I don't know when it is going to be successful or fail. I don't know when to trust it and when not to trust it. And so what we honed in on that specific problem on that particular problem. One of the things that you could look at is uncertainty. So basically, hey, can the model itself express when it is likely to succeed and fail? And so this is not just, I talked about object detection a lot here, but it's also a problem for really a lot of the autonomous systems or AI systems that are out there throughout the DoD and the IC community. So yeah, I think it was largely customer driven, but it was, when I say customer, I mean these, within the people we collaborate with in the DoD. But really, it sort of speaks to like a fundamental problem I think people are considering when actually realistically deploying these systems and be able to reason about when they will succeed and fail.
Thanks, Eric. And when I kind of look at your presentation and I look at who's going to be using the system, I see that definitely as an end user, I would really want to see the uncertainty and the errors, right? So I know what to do with what the machine learning is telling me. I was wondering, are there any other people that are going to benefit, or any other users or any other people in the AI ecosystem that'll benefit from quantifying uncertainty or identifying the errors?
Yeah, a lot of the talk focused on mainly, like you said, like the end users. So while the model's being deployed, someone's actually using or looking at the predictions made from a model, in this case, an object detector. How can they reason about, uncertainty or errors, right? But really, another use case is for the actual engineers or developers of the ML system themselves. So say you're taking an ML model you trained and you've tested in the lab or in some sort of controlled environment. Now you're trying to deploy it, right? So that transition from in the lab to deployment, it's rife with assumptions that were made that could be broken. And so really using these estimates of uncertainty to reason about the situations which the model is likely to fail and succeed, allow you to quickly identify these failure modes to be able to iterate your model on. So this can include things like, hey, we need to collect more data in this particular set of instances because our model tends to be failing at night or in the rain or things like that. Your model's being able to express uncertainty situations, allow you to identify those specific use cases or those particular scenarios and say, hey, we need to do something with our model, like collect more data to rectify those particular scenarios. And that's just one of them, but really, building, a testing apparatus, a test and evaluation apparatus, that includes things like quantifying the uncertainty in the models, allows you to potentially, go from the lab to deployment quicker, and potentially build these more robust systems from the point of view of these engineers that are building the systems.
Oh, that sounds pretty cool. So it sounds like you don't need to wait till these things are in production to figure out if they're going to fail or not. You could use these methods to actually see if there's going to be issues before you go to production and before it goes in the field.
Yeah, I mean, I think there's no, obviously I don't think there's any silver bullet that's going to solve all of the problems, but I think part of a larger testing suite of just sort of a well-rounded testing of an ML model can include, and probably should include, some notion of uncertainty. If the model is able to express in the testing environments when it's unlikely to, when it's not sure about its predictions, this is something that's could be useful information as you go to to production, as you go into deployment, right? You can potentially identify errors that you wouldn't have seen before by having this ability to test or having the model be able to express uncertainty in these ways.
Very cool. Cool. Can you talk a little bit about what else is going on in the field of uncertainty quantification?
Yeah, there's actually a lot. It's when we started this project 2 years ago, I would say, we were just catching, maybe the first wave of the research that's coming through. There was an increased interest in this from the academic community. Maybe a year or so from when we started working on this a couple years ago. And since then, there's been a lot of different ways that people have studied this problem. And so we talked about using the estimates from the predictive uncertainties out of a model to detect errors. There's also building models that are able to express errors in different ways. So not just whether the model is likely to make an error or not, or this uncertainty in the predictions, but the source of the uncertainty. So saying, hey, is my model uncertain because of I don't have enough data, right? So my model hasn't seen the right data for this point. Or, hey, is there just noise in the data? So having your model be able to definitely say one versus the other, and as opposed to saying I'm uncertain, that's something that's been studied on quite a bit. We work on a little bit in this project on a separate part of it, but we also another really important problem is discussing or having your models reason about instances or inputs that are just entirely out of the distribution of your training set. So this could be things like, hey, our model was trained, entirely on sunny days, but then when we, go to deploy, we have to work at night, right? And so this represents a shift from what you trained on your model on to how it's deployed, right? How you're able to be, robust to that, or even just reason about whether your model is able to is in that particular setting where it's different than your training data. The most extreme case of that is when you have instances of classes you've never even trained on. So in the example, I talked about cars and pedestrians as an example, but I also used the idea of these trucks that are driving by. So imagine you're trying to detect trucks and people and things like that, and then suddenly that's what your model's able to reason about. But then you see an airplane or some other object that you've never trained on before. Simply identifying that your model is unable to reason about that new class is something that is an active research subject and something that we're working on in this project.
Mm-hmm. I guess kind of related to that, we had a question come in hot off the press. So the question is, what is the state of the art in detecting outside the design domain condition?
Yeah, I think so. As I understand this, and pop in the chat if this doesn't answer your question. When I hear design domain, I think about all of the design decisions that go up through training a model. So this includes like choice of model, or like in deep learning, this would be choice of architecture. This would be, obviously the thing I've been talking about is training data. In a lot of ways, the training data defines the domain of the problem, right? I talked a little bit about out of distribution detection. So this means like if your data, that's if your design space in this case is going to be defined by the data, detecting if your deployment scenario is different in the forms of data it sees than during train time. Obviously, this is relevant to the out of distribution detection stuff I just spoke about that we're working on in this project, but also things like hey, is there inherent biases in neural network architectures that make them ill-posed for certain problems? I know other folks are working on those types of problems and other design decisions like choice of architecture and how those actually affect your ability to generalize or how to define the domain or design space. Those are all active areas of research. We focus on the one thing in terms of data because it's something that's I think really easily testable and really is something that a lot of people, it resonates with them.
Well, thank you, Eric. Well, we appreciate you coming by and sharing your research with us and teaching us about uncertainty in machine learning.
Thank you.
With that, we'll move on to our next speaker. Our next speaker is going to talk to us about machine learning on the tactical edge. Dr. Scott McMillan joined the SEI in May of 2013 and is currently a principal member of the technical staff. Scott currently leads research in the advanced computing portfolio for graph analytics, machine learning, and artificial intelligence workflows. He is the member of the GraphBLOS Forum and an author of the GraphBLOS C API specification. His current research in the area involves the development of a C++ API specification and the development of high-performance parallel and distributed implementations. He brings over 25 years of experience in high-performance computing across a wide range of application areas, including scientific computing, 2D, 3D, geographic information systems, and very large-scale graph database systems. He also has a ton of expertise in the C++ programming language, object-oriented software design, and guiding the entire software development lifecycle using agile methodologies. Here's Scott McMillan talking about portable high-performance inference on the tactical edge.
Hi, I'm Scott McMillan, Principal Investigator for a project called Portable High Performance Inference at the Tactical Edge, or FIGHT for short. This is work sponsored by the Department of Defense for the funding of the Software Engineering Institute at Carnegie Mellon University. FIGHT enables AI for decision-making advantage at the tactical edge by addressing some of the problems with AI software. It is computationally expensive and requires extensive knowledge, skill, and effort to adopt for low-power devices at the tactical edge. Our solution is to develop an open-source library of machine learning algorithms that are optimized specifically for these types of devices. With the successful conclusion of this project, we will enable rapid adoption of new and novel embedded hardware architectures that would aid in deployment of machine learning across a spectrum of edge-based applications. Efficient use of this hardware will enable longer operational times that lead to increased situational awareness and force protection. Less weight can result in increased mobility of these devices. We are engaging a U.S. Army stakeholder called the Atlas program. The Atlas program is an infrared targeting system. Infrared camera provides a video feed to an AI algorithm system that provides object detection and image classification functions that then feed targeting systems to aid in manual targeting operations. This is an example of what the Atlas system could look like. On the right is a video feed from an infrared camera. The object detection system scans the scene and looks for objects of interest and puts bounding boxes around them. That's the red rectangle on the right. The image within that rectangle is then fed to image classification to identify the object that is in the scene, in this case, a tank. This is an example of video imagery from a publicly available data set called Automatic Target Recognition. It contains 300 gigabytes of full motion video that contains different types of objects in the scene, including tanks, armored vehicles, trucks, and even people. This is an overview of the computing landscape that we're dealing with. On the left is the NVIDIA DGX2. It is dubbed a supercomputer in a box. That system is usually a rack-mounted system in a data center that is used to train neural network models. We, on the other hand, are trying to target lower power and smaller form factors that you see on the right, ranging from the Jetson Xavier in the middle all the way down to a Raspberry Pi Pico microcontroller on the right. Compared to the DGX2, these systems take significantly less power, on the order of tens of watts down to hundreds of milliwatts, cost a lot less, from $1,000 down to a few dollars, and has significantly less memory and compute power available to compute machine learning models. Our goal in this project is to push as much analytic capability to the right. So our approach is to partner with researchers in CMU's ECE department. The Electrical and Computer Engineering department does much research in performance engineering, mapping software to various hardware architectures. This is an example of one of their papers that we are addressing in this project on direct convolution resulting in zero memory overhead. Specifically, we are partnering with Professor Zimeng Lo, a co-author on that paper, and his graduate students shown here in this slide. So a little bit about the library that we're developing. It's called Software for Machine Learning Libraries, or SMAL for short. It has an innovative architecture. We are defining 2 application programming interfaces, or APIs. A high-level API is provided to machine learning developers. This API contains many common operations found in convolutional neural networks that are used in image classification, object detection algorithms. We also define a low-level API. The purpose of this API is to achieve some form of performance portability. This API defines low-level microkernels or codelets that need to be implemented for specific hardware targets. If we keep this API as small as possible and the computation as simple as possible, we can speed adoption or porting of this software to new hardware architectures. So in our approach, we're prioritizing support for the models used by the ATLAS program, object detection and image classification models. We use these applications and other benchmarks as driving applications for the development of this library. So at the high-level API, we're focusing on those layers that are found in those types of neural networks. Those are mainly convolutions of various types, including 2D, depth-wise, and fully connected layers, as well as max pooling and a variety of activation layers. Right now, we have 6 of these layers implemented. And with those 6 layers, we can target a number of open source benchmarks. This is a list of the benchmarks from the MLPerf community for tiny and mobile platforms, which are on the smaller end of the scale being targeted here. You'll notice that we have 7 of the 9 benchmarks covered with those 6 layers that I defined on the previous slide. With the addition of a new layer called upsampling convolution, we can also get an 8th benchmark done. But if we want to do language processing applications like mobile BERT, that will require some additional work and is not a priority currently in the FIGHT project. So moving down the stack, I want to address the next layer in the SMAL library, the software for machine learning libraries. This is the orchestration layer. And this is where we apply the recent research in direct convolution. The purpose of this layer is to manage the data coming into and going out of each layer. And it also orchestrates the computation, i.e. the order that the computation happens to produce the output from the input. This slide gives you an example of what a convolution layer might look like. It has a set of input images in the input tensor, and it has a bank of convolution filters. These weights were trained by a much larger neural network training system. They are loaded by the SMAL library, and then it manages the order of computation, computing the input tensor with the weights to produce a set of output tensors, shown on the right. The code on the lower right is a simple implementation or straightforward implementation of a convolution. It is 6 nested loops. The details are unimportant. I just want you to get a feel for what a computation that does this looks like. So with the direct convolution paper, which has been the focus of the first year of this project, is to implement a variation of what I just showed you. In direct convolution, it specifies a custom data layout instead of using packing. This saves memory, but also the purpose of it is to block the data that makes it more efficiently usable by the memory hierarchy found in a variety of systems. And then with that blocking structure, you define the direct convolution loop nest, which ends up being more computationally efficient. That loop nest looks like this. It's more complicated, but remember, you get higher efficiency. Instead of 6 loops, now you have 9. And with those 9 loops, we've defined 3 new tuning parameters. These are knobs that the developer can use to set the blocking size that makes it more efficient for the memory architecture that you're targeting. So each architecture may have a unique set of 3 parameters. A lot of our work is devoted to finding the right set of 3 parameters for the hardware platforms that we're targeting. So beyond direct convolution, we are extending that research to investigate ways to fuse layers now. So in image classification, object detection, neural networks, there are a number of layers. Often there are multiple convolution layers that occur successively. And if you can merge the computation of a pair of layers in the network, you can save memory and possibly reduce computation. This is an example of one such fusing of 2 convolutional layers on the right. I'm not even going to try to explain what that looks like. I put it up here for comparison with the previous couple of slides. And this shows the results of fusing a pair of convolutional layers. So one of the benchmarks that I discussed earlier is MobileNet for image classification. Inside that neural network architecture, 1-by-1 convolutions are next to 3-by-3 depthwise convolutions. This is an example of what the small library can do when you fuse these 2 layers together. And we've compared to some popular neural network architectures in the open source community. So in the vertical bars is runtime to compute one image through this pair of layers. The blue bar is libtorch, which is a C language library. And the purple bar is PyTorch, which is the Python equivalent of libtorch. They require about 1.5 milliseconds to compute. PyTorch is slightly slower than libtorch. In this case, lower is better. The yellow bar is the TensorFlow framework that has been processed by the XLA compiler. So a number of optimizations have been applied, and it performs better, less than 1 millisecond. The green and red bars are what the small library can do with these 2 layers. The green bar is performing the computation with the 2 layers unfused. The red bar is when you fuse the layers. Now you'll notice that there's a slight performance degradation when you fuse the layers. But what the benefit is of the red bar, or the fused version, is the memory savings. And that's what the line is showing in this chart. So for 3 different sets of blocking factors, we can save anywhere from 300 kilobytes to 500 kilobytes. And that's very significant given the small form factors and the small memory footprints that the devices we're targeting have. In general, we can achieve anywhere from 1.5 to 10 times memory reduction over libtorch and TensorFlow. And we can achieve anywhere from 1.2 times to 20 times performance over these 2 popular platforms using this approach. It's very promising work. So we get to the bottom of the stack of the small library, and that's the microkernel API. This is low-level code. Generally, what happens is the innermost loops of the loop nests I described before define what the microkernel should be. So the orchestration layer will take those last few loops and call into the microkernel API saying, I need you to compute this. Those microkernels, and there are only a handful of them on the order of 10 or less, that need to be written specifically for the hardware that we're targeting. Quite often, the compiler systems optimizers don't do a great job of producing the most optimal code. So often what has to happen is resorting to assembly language. Once we have the microkernels, we develop performance models for the hardware. So we search the space of blocking factors to find out what are optimal for the microkernels for a given hardware architecture. Those blocking factors are then used as part of the kind of microkernel API for the orchestration layer to use when they're performing computation, and that's how we get performance. By keeping the number of microkernels low, we can speed the development of hardware-specific versions of the small library. So we do have a couple of publications. One's in flight right now. We did publish a paper that dealt with some of the microkernel development back in May at IEEE's Parallel and Distributed Processing Symposium. It's how to develop the microkernels when a particular piece of hardware has a special thing called a matrix engine, which is becoming more pervasive in the processor market. In addition, we've submitted a paper on the small library itself to a special issue on TinyML at the ACM Transactions on Embedded Computing. So we are done with 1 year out of 2 on the FIGHT project. And so what's going to be happening over the next year is to develop the microkernels for the Atlas hardware and benchmark what the results are. We will be adding support for more neural network layers to increase the applicability of small to more and more models. And we'll be implementing all the possible fused pairs of layers. And then from that, we will then provide this software as an open source release sometime in this fiscal year. In addition to that, we're also exploring the integration of the system with the MLIR compiler ecosystem. A lot of what we do is what could be automated by a compiler system if they knew how to follow the process that we do to come up with the microkernels and the blocking factors. And with that, I'll open up for questions.
Hello, I'm here with Scott McMillan, and we'll have a chance to ask some questions from both myself and the audience around his research. I'll start off. Scott, so what's more important to current stakeholders, higher performance with current hardware or the same performance with new lower power hardware?
Well, I would say that both are a priority, but in a particular order. So right now they're concerned about performance. They have existing systems and they want to do more with them. When we're talking about looking at lower power and using less memory and things like that, which this project is also addressing, that's really going to be a concern when they're trying to pick hardware for the next generation systems. And so they're going to try and fit the same capability into lower swap constraints, so size, weight, and power, and then this work will have benefit in that area as well.
Let's see. And what do you think about the current hardware? Is there a lot of new hardware coming down the line, or is there a big need to create new hardware to accommodate the need in the future?
Well, I think there is a lot of hardware coming down the line because there is a great need to create that hardware. The workloads are getting complex, and if you want to compute in real time, you have to have very specific circuitry. And we were seeing a lot of hardware designs coming out of say DARPA programs that are directly addressing neural network circuits that can compute faster with lower power. We could create microkernels for those types of hardware as well, so that we can have an abstraction layer on top of that hardware and they could adopt that hardware a lot faster.
Oh, that's very cool. That's exciting that there's new DARPA type hardware coming out. I used to only hear about those in the movies, so it's cool to see that in real life. Another question is, the work that you're talking about seems to be pretty low end, or small devices. Will this kind of work be applied, or is it useful for our high-end processors as well?
Oh, sure. I mean, we can sit there and do performance modeling for any type of hardware and handwrite the microkernels for those architectures as well. The challenge is that there's a lot greater competition in the software space at those levels. The current neural network libraries are very mature, and a lot of similar type efforts have gone into optimizing those libraries for the pervasive hardware such as Intel chips and AMD chips and things like that. So the gains would probably be more modest, but I do believe that there are some gains to be had because they're not using some of the more recent research in direct convolution that saves memory.
Mm-hmm. And speaking of like the Intel chips, do you see that they're going to become more and more ML focused in the future, or how do you see those evolving?
Yeah, I'm not one to speculate on the direction of markets. I'm probably the worst person, but I do see the chips becoming more complex. I do hear about architectures that include FPGA elements or configurable elements, and I just think there's going to be a lot of opportunities to provide a software architecture like this that can abstract away that increasing complexity that we're seeing in hardware.
Yeah, tons of opportunities, but it also sounds that it needs a lot of specialized expertise to take advantage of this kind of stuff.
Yeah, that's right. There is a requirement still for performance engineers, those folks that understand low-level software and how it interacts with hardware. We're just trying to minimize the amount of work that needs to be done with this type of architecture.
Mm-hmm. How about another modality is distributed computing systems? Can this approach be used for distributed computing as well?
So as the small library stands right now, the application of the library would be on a per node basis. So this software applies, when you're doing computation on any one of the distributed compute nodes, you're going to need software like this. We're currently the distributed layer, that very top layer about how to do data structures across nodes and in different memory domains is not in scope with small right now. If there is a demand for it, then we can certainly look into those aspects at a future time.
And in terms of this small library, how will small be released? Is it going to be something that's maintained or expanded?
Yeah, so the plans are to release it as a GitHub repository, and we're probably going to release the first half of next calendar year, at least a beta. And as we add capability, specifically more opportunities for fusion between layers, we'll be doing re-releases. I plan to take a role in providing some software engineering, so testing, API design, and things like that to make it useful. But we also have work, again, in the MLIR space to see, how this type of software approach could be integrated into compiler stacks specifically for ML workloads.
Sounds like there's a lot left to be done. Is there anything where the community can help or ways that people can get engaged in the project?
Well, I would say that after the software is released, I mean, anybody has access to it, can issue pull requests if they want changes, they can submit issues against things that they would like to see done. The project hopefully will take a life of its own after the release and initial adoption.
Cool. And another thing that I think is pretty cool is that you're working with campus. For example, I'm on campus today, and we have sort of the world's leading researchers in AI at CMU. Talk a little bit more about your campus collaboration. Is this something campus has been working on for a long time, and what are they looking at?
Yeah, so I work with a group of professors in the electrical and computer engineering department. They are experts in performance engineering, all types of hardware. They have a wonderful showcase of all types of hardware that they go after. They have been working in this space for probably over a decade. Probably, that's my experience with them so far, and it's probably longer than that. The particular research that we're building on was published in 2018, and so they've been working in that particular area of research for at least 5 years, maybe longer. And that work will continue into the future.
Cool. What do you think in terms of some future directions that you're looking at, or some of the priorities that you have for the future? Any thoughts there?
Well, so the immediate thing is to get the library out. We have the individual layers implemented, and we're doing performance evaluations on it right now. We're looking at the initial release with that, and then a very quick release after that with the layers that are fused, performance evaluations with that too. But we are looking at some of the other ML perf benchmarks, and so there is a laundry list of things that we could add to the library to support more neural network models, especially the ones like transformers that are becoming crazy popular in this space.
Cool. Yeah, maybe one day we'll be able to load a small transformer model and be able to have it on the edge or carry one around. That'd be pretty cool.
Yeah.
And then the last question for you is, other than the C5 ISR, are there any other groups that might be interested in this research?
Well, I would say any person that's concerned about swap constraints. So, if they have size, weight, power constraints, or they have devices with limited memory and they want to do more with it, I think small is a viable option in that space. And so, I could think of applications in spaceborne sensor packages or drones or, unattended sensors anywhere.
Yeah, I see that this space is something that has a lot of space to grow. I see that we can create these devices that can be configurable. So imagine creating a box that could be reprogrammed. You can carry it around. They can do mission specific, or in our personal cases, personal specific applications like chatbots, or we can carry it around and use it to identify, say for example, where did I lose my keys and where's my car? So a lot of space in this area. So with that, I wanted to thank you, Scott, for coming and sharing your research with us.
Oh, thanks for having me. I appreciate it.
And with that, we'll head over to a short 15-minute break. We'll resume at 2:15. And then if you'd like to stay engaged, we're going to have a series of shorts that illustrate some of the work that we're doing at the SEI.
Organizations often struggle with moving machine learning components into production systems because different teams work independently during different stages of system development. For example, data science teams develop a model. These teams then pass the model to a software engineering team for integration and testing into the machine learning system, and finally an operations team deploys and monitors the ML system. Because these teams often work independently and without any system or mission context, they tend to make incorrect assumptions about decisions that other teams and stakeholders have made, leading to what we call ML mismatch. As DoD and organizations adopt machine learning to solve mission-critical problems, the inability to detect and avoid ML mismatch creates delays, rework, and failure in the development, deployment, and evolution of ML systems. In this presentation, I will discuss and demonstrate TEC, a tool that detects ML mismatch by using a series of descriptors that define information that teams must share to avoid ML mismatch. I will also show how we are extending and using the descriptors to support testing of ML components for production readiness, which is a major challenge for fielding production ML systems that meet mission and system goals. You don't want to miss it.
Hi, I'm Mike Conrad, Principal Researcher at the SEI, and I'm here to tell you about our one-year project to apply causal discovery and inference to determine how robust AI and machine learning systems predictions are to particular mission and environmental changes. AI, or machine learning systems, can provide a significant edge to the DoD. However, in rapidly changing environments and settings, these systems need to be closely monitored to determine when they need to be retrained. In tackling this challenge, we had two goals. First, develop an approach for determining when AI and ML systems predictions can be trusted in changing contexts. Second, build an application for evaluating the robustness. The particular domain we chose for our project was engine health. In stage one, we prototyped a scalable cloud application for evaluating classifiers using labeled data. The engine analyst specifies a particular classifier in a particular subset of the data to be used for evaluation. The application trains and evaluates that classifier on that labeled data and then generates classifier performance metrics. The engine analyst can then repeat these steps with other data and classifiers. In stage two, we considered unlabeled data, data that doesn't say whether the engine is healthy or not. representing a novel or stressful situation. We applied causal discovery to derive a causal graph and then causal inference to identify and estimate the average causal effect on engine health. In this way, we calculate labels for the previously unlabeled data. Then, using this now labeled data set, we can apply the application just described in stage 1 to estimate classifier accuracy in the new situation. Beyond engine health, this capability could be useful in any organization that maintains fleets or groups of DoD systems whose health must be continually monitored in changing conditions. This project is also part of a longer, broader term effort to apply techniques developed elsewhere, for example in epidemiology, to DoD systems to improve the effectiveness of ML and AI systems. Our goal is to do this in multiple settings and demonstrate the value these new technologies will have in other domains. We collaborated with researchers at Columbia and Carnegie Mellon universities, and their algorithms contributed to our success. If you're interested in better monitoring your fleet's performance and understanding the limits of AI and ML in your context, we would love to work with you. Just reach out to us at info@sei.cmu.edu.
More than 3 billion images and more than 700,000 hours of video are uploaded to the internet every single day. How can anyone detect fake media and do it quickly? Hello, my name is Dr. Shannon Gallagher, and I'm a machine learning research scientist at the Software Engineering Institute. My team works on detecting deepfakes, believable media that are generated by deep neural networks. While deepfakes can be used to impersonate political figures and celebrities, they can also be used to deceive or defame anyone. Deepfakes are even becoming recognized as potential weapons in armed conflict. Our solution is a deepfake detection pipeline. This pipeline is an end-to-end process that creates modular, reproducible, and portable deepfake detection systems, as well as benchmarks. Many deepfake detection systems integrate data collection and transformation, neural network implementation and training, and evaluation at both computer and human levels. This is because, ultimately, deepfakes are intended for consumption by humans, not computers. Because we've put all this together into a single pipeline, we're creating more robust detectors that can easily be compared to one another. If you're interested in learning more, please tune in to my talk on machine learning for deepfake detection.
Hello, and welcome back. I'm excited for our next pair of speakers who will continue our focus on forging the path and the accelerated delivery and adoption of AI. Our next talk will be on the mismatches in AI by Dr. Grace Lewis. Dr. Grace Lewis is a principal researcher and the lead for the Tactical and AI-Enabled Systems Initiative at the Carnegie Mellon Software Engineering Institute. She is a principal investigator for 2 projects in the growing field of software engineering for machine learning systems. She leads characterizing and detecting mismatch in ML-enabled systems and predicting inference degradation in production ML systems. Her current areas of expertise and interest include software engineering for AI ML systems, software architecture, in particular the development of software architecture practices for systems, edge computing, and Software Engineering Society. She's also quite active. She's a senior member and a member of the IEEE Computer Society, participating in both committees and conferences. She's a VP for the IEEE Computer Society Technical and Conference Activities Board, member of the Board of Governors, and member of the Diversity and Inclusion Committee, and in addition to a number of roles at ABET as well. I'd like to now turn it over for Dr. Grace Lewis to talk about her work in advancing mismatch detection and system testing for ML systems.
Hello, my name is Grace Lewis, and today I will be talking to you about our project, Automating Mismatch Detection and Testing in Machine Learning Systems. Many studies show, including some that we have conducted, that organizations really struggle when they're trying to move machine learning components into production systems. Some of these challenges include, for example, that the model component performs very poorly because model training data is very different from production data. Other challenges, for example, include that large amounts of glue code have to be developed due to API mismatch between the ML component and the system components. Sometimes production environments and tools are not really set up to detect model problems or to collect all the data that would be necessary for model troubleshooting and retraining. Sometimes systems perform poorly, or you can't even deploy them because the available computing resources in the production environment are really not enough to support model inference requirements. And sometimes it is simply that organizations acquire ML components and they really don't know how to test them properly. One of the reasons for these challenges is that when you think about the development of machine learning-enabled systems, you have 3 different groups of people, 3 different sets of activities, 3 different workflows, and sometimes 3 different languages that are involved. You have data scientists or machine learning engineers are performing model development. Once that model is developed, it gets passed on to a software engineering team to do model integration and testing, and then the system is passed on to an operations staff for deployment and operation. And the problem is that these teams often worked very independently and often with no system context. Even though collaboration across different development teams, especially interdisciplinary collaboration, has been a challenge that has been studied for many years, what I want to do in these couple of slides is give you an idea of why it gets exacerbated when you talk about ML systems. So this diagram here shows more or less what a model development workflow looks like. This is performed typically by data scientists and ML engineers, training in statistics, training in machine learning, but not necessarily training in software engineering. And what happens here is that they often have to make decisions in this workflow without any information about system context, about upstream and downstream components, or even of production data. So as they prepare their data preparation code, as they do feature selection, as they do algorithm selection, as they think about how to package their code, they're basically doing this in a vacuum because no data is available for them. If we look at the model integration and testing workflow, the software engineer receives the model and the data pipeline code, for example, from the modeling team. But now, this code has to be integrated into a larger system. And obviously, they would need information about system context. They would need information about the production environment in order to be able to integrate the model properly. But more than anything, they need test cases and test data to know if the model has integrated properly. And unfortunately, developing test cases and test data is not necessarily part of the model development workflow. And finally, once the system is all put together, now the system is put into production. And operations folks that are in charge of this need to have good information about system context, but they also really need to have information about resource requirements so they can prepare better, and monitor requirements as well, especially if what you're trying to measure is metrics that they're not used to gathering, like, for example, decreasing model accuracy or, for example, drift. And so what happens in these situations is something that we call ML mismatch, which is a problem that occurs in the development, deployment, or operation of a system when people make incorrect assumptions about the other system elements. And these incorrect assumptions lead to a negative consequence. And the real problem here is that as DoD adopts machine learning to solve some of their mission-critical problems, not being able to detect this mismatch and avoid this mismatch early in the process creates delays, it creates rework, and eventually failure of these types of systems. So in previous work, what we did was we conducted an empirical study to try to understand what ML mismatch looks like in practice and what is the information that could have been explicitly shared between stakeholders to avoid this mismatch. What you see on the left side of this slide are the results from our very initial study that found out that this was the information that was needed to be shared, and this was validated via a survey in a survey. So after that, we've gone through several iterations, received a lot of feedback, and what we've ended up is with a set of 8 descriptors that specifically define the system attributes that need to be specified in order to avoid mismatch. So building on this work, the project objectives for the project that I'm going to talk to you about today are to develop a suite of tools to first automate ML mismatch detection. We also want to show how we can extend and use these descriptors to support testing production readiness of machine learning components, and I'll tell you about this in a minute. And finally, to be able to validate research results with DoD systems and collaborators. A theme that you will hear throughout the presentation is that we are looking for collaborators. So if you resonate with the problems that you are seeing, if you would want to participate in the results and receive the results of this research, please let us know, because we are looking for collaborators. In year one of this project, we developed TEC, the ML mismatch detection tool. TEC allows stakeholders to develop and share descriptors for their part of the system and to view any descriptors that are developed by other stakeholders during any time of the development process. In addition, if system elements are acquired from other teams or from contractors, you could also import some of these descriptors into the system. And finally, what TEC allows you to do is at any point during the system development process, you can run the mismatch detection capability, which will show you if there are mismatches between the information that is being provided by all these stakeholders. What you are going to see now is a very short demo of TEC, and it's going to show you how different stakeholders can enter and share information, and also a little bit about the mismatch detection capabilities. Welcome to TEC, a tool developed by the SEI for detection of ML mismatch. TEC allows ML system stakeholders to enter and share information about ML system elements that is essential for avoiding ML mismatch, especially if responsibility for different system elements resides in different stakeholders or teams. This information is categorized into a set of 8 descriptors for each project. TEC forces system owners to think about and provide important system context information for model and system development, such as business goals, available data, and success criteria. Model developers can use system context information as well as production data and production environment information as they make their decisions, while they also use TEC to record data pipelined and trained model information that can be used by others, such as model inputs and outputs and runtime monitoring requirements. Software engineers or system integrators responsible for integrating the ML component into the ML system now have all the information that they need for their tasks. In addition, they use TEC to share information about the development environment with model developers as well as operations staff. Operations staff use TEC to share information about the production environment, such as available computing resources, which is a critical piece of information for both model and system developers. At any point during the project, any stakeholder can run an analysis to detect if there are mismatches between all the provided information across all descriptors. Each mismatch contains rationale information and the specific condition that triggered the mismatch. This information can, for example, be used by system owners to allocate resources to address the mismatch, by model developers to fix problems in their code, or by model acquirers as part of their testing process. The advantage of incorporating TEC early in the ML systems development process is that it brings together all stakeholders and teams and forces them to provide all information that is necessary to avoid mismatch, which can lead to delays, rework, or failure in production. This concludes the short demo for TEC, the ML mismatch detection tool. Please contact us if you have any questions or are interested in evaluating TEC or the ML system element descriptors. Thank you. As we are going into year 2, we are now focusing on ML component testing, which is a challenge. It's a very known challenge for many organizations that is consistent not only with our studies, but with findings from many practitioner studies, which is basically that organizations really don't know how to test ML components. This is a very large space, so what we're doing in our work is particularly focusing on testing production readiness of machine learning components, which means that I develop a model that is ready for production, that is ready for integration into a larger system in operation. And we define production readiness based on a set of attributes. The first one is ease of integration, which basically means that the ML component inputs and outputs match those of the upstream and downstream components in the production system. The second one is testability, which means that the ML component either provides specifications, test cases, or test data that can be used by software developers to integrate the model, or at least provides evidence of either testing or that best practices were followed. The third attribute is monitorability, which means that the ML component produces information that the monitoring components in the system can be used to detect problems. And very related to monitorability is maintainability, which means that the component also defines or even produces data that teams can use for model retraining and troubleshooting. And finally, quality, which means that the ML component meets quality requirements, which we've divided into two, into model requirements, like, for example, accuracy, and system requirements, like, for example, inference time and resource consumption. So to that effect, the end goal of year 2 of our project is to develop an ML component testing system. First of all, we're going to need to extend the descriptors to support testing of production readiness of ML components, as I justified in the previous slide. And our initial testing capabilities are going to be targeted at organizations or quality assurance teams as they perform either acceptance testing or independent testing of these ML components. Why? Because this is where really the least amount of understanding and tool support exists. So with the ML component testing assistant, which is going to be basically a suite of tools, what different stakeholders, in this case QA teams or independent testers, will be able to use to do test case generation, test data generation. They'll be able to profile their models to see how much resources they need in the production environment, and any other tests either that we've developed or that we are using from others that will be able to perform testing and specifically of model production readiness. So where are we in year 2 of our project? Where are we with this task? Something that we've already completed related to model quality is a tool for train test leakage detection. And I will talk about that in the next slide. We have 2 activities in progress as we are building this tool suite that I talked about before. The first one is black box testing of ML component capabilities, where we're looking at generation of corner cases for different capabilities to be able to measure generalizability of the model that is being developed. The second is, and this goes to more production readiness in general, we're working on an evidence-based process and tool for independent testing of ML component production readiness, where we're assisting 2 parts of a process. We're assisting model developers as they introduce evidence into their model code, and we're assisting independent testers as they use this evidence to determine if the model is production ready. With respect to train test leakage detection, why did we start there? We did a study that was looking at challenges in collaboration for organizations that were building ML systems, and a problem that always came up was this trust in models developed by external teams. Why? Because what they reported is that model developers often report high performance during test and evaluation, but the reason for this is because they are overfit, sometimes inadvertently, and sometimes even intentionally. And one cause for overfitting is something that is called train test leakage, which means that information about the test data leaks into the training data. So to this effect, we developed a static analysis tool, and it uses both data flow analysis and pointer analysis, and it detects 3 different types of leakage. It detects overlap leakage, which basically when test data is directly used as input for training or for hyperparameter tuning. Multi-test leakage, when test data is used repeatedly for evaluation instead of a single time. And finally, pre-processing leakage, which is when test data and training data are pre-processed together, often before splitting. As I said before, one of the themes is looking for collaborators. As an applied research and development organization, we need collaborators. We need collaborators to inform our research. We need collaborators to validate our research. In the near term, we are looking for organizations that would be willing to use the automated mismatch detection tool and provide feedback. And we're also looking for organizations or teams, for example, DT&E or OT&E teams, that are tasked with testing machine learning components or systems developed by other organizations. We're looking to better understand what model production readiness means for these organizations, to brainstorm about solutions, and once we incorporate that into our tool, to be able to provide feedback on this. Obviously, in the longer term, our goal is to be able to find organizations that are willing to integrate some of the approaches that we have developed into their own ML system development and testing processes and tool chains. To finalize, this is our team. And these are the publications that have been referenced throughout our presentation. Thank you very much. And now we're ready for questions.
Hello, I'm sitting here virtually with Dr. Grace Lewis, Alex Dare, and Dr. Rachel Brower-Singing, where we'll have a chance to discuss their work. And for those of you who are wondering how to engage with the speakers and ask questions, please join our Discord server where you can chat with other participants, and you can even submit questions for us to answer in this session. So one thing that I was struck with was the last slide where you're actually asking for participation and collaboration. Can you talk a little bit about the expectations for someone who's interested in collaboration?
Absolutely. Thank you, John. So the project has two parts to it, right? It has the part where we develop tech, the mismatch detection tool, and then it has the second part, which is extending the tech tool to support testing. So for the first part of the tool, the tool is ready. We're looking for collaborators that can use the tool, that can tell us about the utility of the value of the descriptors that we're creating, the tool itself. And for the second part of testing, this is research that is more in its starting phase. So we're looking for collaborators to help us shape the research. So to help us define what are the challenges that they're having when they're testing machine learning systems. What are some of the techniques that they use? So it's more of an exploratory collaboration that will eventually also lead to tool evaluation. But I would say for the first part, we're looking for collaborators for tool evaluation. For the second part, we're looking for collaborators to help us shape the research through participation in interviews and in workshops, in joint sessions.
Oh, cool. Just a few follow-up questions to that. What kind of capabilities do people need, or does an organization need to have to use the tool?
I'm going to give that question to Alex.
So there aren't a ton of requirements that are needed to use the tool. It's pretty simple. It runs on a Nuxt.js front end and just a simple Python backend. The code will be open source, so we can provide it to you in a open source format, just give you the source code and you can run it. It runs within Docker containers, so we can also just provide you with the containers themselves. Or we will have a instance of the tool hosted here at the SEI, which you can then use at your own discretion without having to set anything up by yourself.
Good. And just a quick question around that. Will it run on Windows devices, or is it Linux or Mac, or I guess if you run on Docker, you can run it on all of those?
Yeah, so it's any system that supports Docker. So really any of the major three, you should be good to go.
Cool. Another question that I was kicking around in my head is around that testing part of the project. Why did you decide to focus on model production readiness, for example?
Right. So obviously testing is a very, very wide field. And so one of the challenge we've done 2 empirical studies prior to what we're doing now. And one of the biggest challenges was really putting models into production. So a lot of people have a lot of experience developing models, but getting them out of the labs and into production has been a big challenge. And in particular, when it comes to testing. There are techniques out there for testing, I would say, the model development stage, model experimentation stage, but there is not a lot of support or even understanding of how do you test that model before it goes into production to make sure that it's production ready. That especially when you're developing across teams and you have a model development team building a model, and then, for example, passing on to model to a software engineering team that now has to integrate it. So that piece of that piece on how to do that testing, how to do that form of acceptance testing, or knowing just that it's ready for production, that is probably one of the most unexplored areas there is, and that's why we decided to address that particular challenge.
Interesting. And when you think about the challenge and the tool, and then how it helps, is it something that the data scientists are pretty happy to hear, or the software engineers are happy to hear? I guess, is there just a lot of conflict in the process that kind of gets resolved through this?
Right. So I can provide you the software engineering perspective, and then my colleague Rachel will provide you the data science perspective. So from a software engineering perspective, the challenge is that if, for example, if a data scientist hands me a model or say, hey, it's ready for integration, I would say as a software engineer, I'm not sure what to do with it. It's like, because I have to do integration testing. It's like, okay, so like, what data do I give it? How do I know that the upstream, the downstream and upstream components are ready for it? So I think that what we're doing is really going to be helpful for software engineers from that perspective, just knowing just what to do. It's just so that I can integrate into a system. And Rachel, from a data scientist perspective, what do you see? What is the value that you see of what we're doing?
From a data science perspective, I see that there's a lot of value in starting to provide a common framework and a common lens of communication so that you can take your model and then give it to a software engineer and have a common ground with which to talk about this is what we need to make this model operate in production. And so it's how do you start to discuss that, and then actually starting to provide this is the evidence, or these are the data sets, or this is how we should do testing from this side, and then being able to combine that with how testing is done on the software engineering side.
Mm-hmm.
Yeah, it sounds like there's a ton of opportunities to improve the collaboration. You know, they're not speaking the same language. Models are getting thrown over the fence. The software engineers don't know how to test them. So it seems like there's a ton of opportunities here.
Agree. We see them a lot.
Another thing I saw in your presentations, and you know, for those of you out there on the interweb, feel free to throw in some questions for the speakers. There's a lot of component attributes that we're trying to go after. We're going after ease of integration, testability, monitorability, maintainability, quality, and sometimes these things are at conflict. How do you wrap your head around having so many different objectives or attributes that we're working off of?
Right. So right now, because the research, that part of the research just started in this quality attribute. So what we've done has been pretty opportunistic. So like one of the studies that we did before showed that train test leakage was a problem. So we said, okay, great, let's build a tool around that part of it and provide it to data scientists to test for train test leakage. But going forward, again, this is why we're really trying to get collaboration for this part, because like you said, for example, we defined, production readiness in terms of a series of attributes, but they might be in conflict. And to be honest, this is how, when you're architecting systems, that's very common, right? You favor this quality attribute at the expense of this other quality attribute. So getting together with people that are testing these types of systems, that are having these challenges, that are maybe experiencing some of the collaboration problems that you talked about, is really going to help us define which attributes do we go after first, so we can focus on those. But always as we're developing our solutions, keep in mind that there are others that are going to be in conflict and how we address those. So, for example, another parallel effort that we're doing in for this particular project is building more of a, what I would call, an evidence-based tool, where what we're trying is not necessarily to do the testing part, but provide evidence even within the code that somebody can extract information from and say, okay, I have confidence that this model is going to perform well, or is going to do well, or is going to integrate well because they've done these tests, or they followed these practices, or things like that. So in the evidence, providing evidence-based, at least that part kind of gets a little bit away from having to prioritize and just looking at just the evidence piece. But I agree with you that those are in conflict. And this, again, I mean, we're really looking for collaborators. We want to find out what is it that people are or finding challenging when it comes to testing.
Yeah, that sounds really attractive. Like, say, for example, I'm an organization and then I want to collaborate with you. How would that look like? Is it a visit? Is it an interview? Is it a workshop? Or would it be kind of like a small project?
It can be any of the above, because we understand that different organizations have different priorities, different times, different ways that they can collaborate. Ideally, what we would prefer would be something of a workshop setting where we can actually get together, get people outside of the office and really focus and sit down with us. But we're very open to doing interviews. We can do that. We can do interviews one-on-one. We can come visit you. You can come visit us. Anything you want to do. Ideally, workshop, but we'll settle for interviews.
And that makes sense. In terms of like who would you get access to, would you which groups would you need access to? The data scientists, the platform folks, or any particular priorities or thoughts on who you'd want to talk to and have in the workshops?
Right. So ideally, what we would like to have is people from organizations where their different activities are separate, because this is where we find the most challenges. But that's actually very common in DoD, where you have model development groups, and where you have software engineering groups, and you can even have separate testing groups. So I think those are the groups that would be best suited for us to work with, where that development is separate in that way. Also, it would be great to talk to DT&E groups, for example, to the development, test, and evaluation. Because those are the folks that are potentially going to receive these models and it's like, okay, they're ready here, go do the testing. And so those types of organizations would also be interesting because they wouldn't provide the collaboration perspective necessarily, but they would provide like that challenge perspective of saying, okay, yes, I just received a model. What do I do with it? Which is what we're seeing a lot of people struggling with.
Yeah, that sounds pretty cool. And what would they get out of it? I mean, would you be sort of like a ML systems therapist and provide, kind of feedback, or would you give very concrete feedback? Yeah, if you're to think about, well, I'll bring you in, but then I have to explain to my boss, what do we get out of it? Any thoughts on explain that?
Sure. So as a research and development center that we are, I think that the biggest advantage the organizations get out of working with us is really getting to shape the research, getting to define the research. Like if we're addressing your problems, it's going to be more appropriate to your problems once again. So getting to shape the research, I think, is one thing. The other one is obviously early access to results, because if you're going to help us shape the research, obviously you would be the first ones to get access to the results that we have. So receiving that, trying to get ahead of the curve. And obviously, I mean, it really depends on the organization. We've done publications with the organizations, assuming that, for example, the organization is willing to do that. So there are different things that the organization can get out of it. But I think most of all, it's early access to research results.
Yeah. I guess the question came in from the audience, Rowan. Do you recommend automated testing for ML, T&E, or a mix of stress testing with TA?
TA as in probably automated testing, right?
Yeah, I can take my best guess, but maybe you should take yours.
Okay. Yeah. So do you recommend so once again, the answer to that is one that unfortunately is very common, but it really is it depends. There are some parts of testing that can be automated. So for example, if you were to do unit testing, right? Like the traditional, I would say, unit testing that you do in software engineering. So one thing that you would do is do, for example, equivalence testing or boundary testing, where you would just test at the boundaries, equivalence classes, and things like that. That is something that could definitely be automated, and actually we're already working on that. But there are other stress testing actually is something that you could also automate as well, because to do stress testing, you don't necessarily need to have you're not looking for accuracy, so you could really just stress test with even with synthetic data or created data, so you can do that. But for example, doing automated testing for something like let's pick another quality attribute, like automated testing for performance, or for one of the more like, I don't know, and it's gonna might be complicated because you might not have the right data to do that kind of testing. So I guess the answer is you can do automated testing as long as it's not necessarily data dependent. But if the results of the test depend, for example, on the quality of the data and things like that, it might be more difficult to do automated testing, because now you have to think about how you generate those data sets that you're going to use for automated testing.
Thanks. Might take a look. I guess we're kind of out of time. We don't have enough time for another question. So with that, I'd like to thank you, Grace, Alex, and Rachel, for sharing your thoughts on ML mismatch. And I'd like to move on and talk about deep fake detection with Dr. Shannon Gallagher. So just to introduce Shannon, Shannon is a data scientist at SEI. Her interests include modeling, uncertainty quantification, and data visualization. She joined the SEI after the completion of her postdoc at the National Institute of Allergy and Infectious Diseases, where she worked on statistical modeling of infectious diseases, competing effects analysis for the ACTT-1 COVID-19 trial, and analysis of statistical tests in low event rate settings. Prior to that, Shannon received her PhD in statistics at the Carnegie Mellon University with an advisor, Bill Eddy. She studied statistical properties of agent-based models. Let's turn it over to Shannon for her talk on a machine learning pipeline for deepfake detection.
Hello, my name is Dr. Shannon Gallagher, and today I will be talking about a machine learning pipeline for deepfake detection. But first, I'd like to introduce you to our team, which includes myself, Dominic Ross, the multimedia design and communications lead, Jeffrey Mellon, a machine learning research scientist, and Catherine Bernachak, a senior machine learning research scientist. So for about the next 20 or so minutes, I'm going to be talking about deepfakes, which according to this Mirsky and Lee paper are believable media generated by deep neural networks. Now, deepfakes are something that we've heard often about in the news lately, and it's something that we've been interested at the SEI for quite a few years now. Now, one thing we like to do at the SEI is make our research available to the public in what capacities we can. And so this includes a webinar, a podcast, and a blog post, and all these links will be available online. So the problem at hand, deepfakes are dangerous and can be a threat to national security. So let's just take a look at the left-hand set of images for a second, just to go over what is going on in a deepfake. So on the left-hand side, we have this woman, and this is going to be our target. She is the person that we want to impersonate through her mannerisms and her speech. The woman on the right is going to be the source. You can kind of see they're sort of similar, and that is very important for making a realistic looking deepfake. So the source is a person that we're able to control through their thoughts and speech by having them follow those directions. And so what we do with a deepfake, a face swap, is we would take the woman's face on the left and place it on the woman's face on the right. And so when you do that, you kind of get the result in the third image at the bottom. And in that way, it can look like that the target is saying the things that the source is actually saying. So potential dangers, of course, include impersonation of political figures and celebrities. So one of these includes, very recently, an impersonation of the mayor of Kiev, where reportedly there was a deepfake of the mayor of Kiev who gained access to European mayors. And there was about 10 minutes of access where the mayor of Kiev was talking to these other leaders, and people could not determine that this was indeed an impersonation. So obviously this is a danger. But there can also be defamation of normal citizens, and deepfakes fall under the umbrella of mis, dis, and malinformation. To give you some context, there are about 700,000 hours of video that are uploaded to the web every single day. And so the question becomes, how do we make these fast and reliable detectors? To give you a little more context of what's going on in deepfake detection methods in academia, a lot of methods already exist. There was a big boom around deepfake detections around 2017, 2018, and if you just type in Google Scholar, deepfake detectors, you're going to get thousands of different results. And so we've read quite a few of these papers. A number of these review papers detail over 100 different methods. So it really becomes a question of what's working the best and on what sort of data are these working the best, and what do we even mean by working the best? And so academia isn't the only one interested in this, however. There was also a Kaggle competition in 2019, and within this competition, there was $1 million prize. So it garnered a lot of interest. And I'm showing you here a GitHub repository from the winner of this competition. So there's actually code available that we're able to follow that we know work very well for this scenario in the deepfake detection methods. So between all these papers and some of this code that's available, we have a pretty good baseline of at least methods to follow and kind of determine what's going on. But reproducing the results is difficult. And this is not because of a matter of bad code. It goes much deeper than that. For example, there are different data formats, and this goes, again, beyond a JPEG versus a PNG when we have an image. This is looking at wide or vertical set cameras, different resolutions, and the face can appear in different framings of the images. So all of this adds together to make deepfake detection very difficult. After that, you also have sparsely documented code. And this just happens when we don't have production level code and people have been working on it, and it's just something we have to work around. We also have a lot of active development going on with packages like OpenCV2, Pillow, and other packages that are used for image processing. Along with that, we also have the backends that we use for deep learning, like PyTorch and TensorFlow, that are used very differently and have been changing over the past few years. So if we try to run a method from 2019, it can in fact be very different. Also, we have hardware. So even trying to run these methods from one machine to another can be very different due to the different GPUs and how they behave. So the best methods try to alleviate these with a Docker container, but even those run scripts we've had to fiddle with to be able to reproduce results. So the takeaway, it is very difficult to compare these numerous methods side by side, and we really came to the conclusion that we need a better system to make benchmarks to compare which methods are more reliable and fast. So our solution here at the SEI is our deepfake detection pipeline. And we made this specifically to make these benchmarks. So our pipeline, you can take in different sets of data and use a plug-and-play detector to use your favorite methods to output results from both training and in testing and feed those into your favorite statistical analysis programs. So DDP is reproducible, portable, and modular, which makes it very useful for creating these benchmarks, and eventually we'll use it to make improved detection systems. One thing that we want to mention is that DDP's backend is SEI's Juneberry, which just had a new version release, and that's a publicly available tool and can be used for other machine learning projects as well, although here we have tailored it to our use case of deepfake detection. To give you an idea of what sort of data exists in this field, we're showing you some of the different publicly available data sets that we've used in our detectors. And this is just a small subset. So the gold standard in the area is this deepfake detection challenge data. And there are over 100,000 10-second clips in this data. So it's quite a good amount of data. However, there's only about 4,000 unique actors in the videos, and a lot of those 100,000 comes from different pairings of faces, the face swaps that go from one actor to the next. But this does include real and fake data and is very, very important for our methods. Another one that's similar to DFDC is this Celeb DF, and it is of a lower resolution, just mostly because it's a bit older, but it has 5,600 videos of different celebrities and includes real and fake data. On the image side, the still image side, we have the StyleGAN family, and specifically I'm showing StyleGAN 3 here, but there are other types of StyleGANs as well. And StyleGAN's pretty interesting because this isn't making face-swapped individuals. StyleGAN 3 actually generates synthetic individuals, so you can generate as many of them as you want. So this is very useful for us as well. So these are all deepfakes. And then we have Flickr Faces HQ. Flickr Faces HQ is a fascinating data set that includes 70,000 portraits of real individuals. It's very interesting just how prevalent the Flickr Faces HQ is across the fields. And when people are working with human faces, you will see this data set come up so often. So it's hard to separate Flickr Face HQ from some of these methods. So to give you a look into some of the data, what we're really trying to do with these detection systems is that we're trying to find the differences between the real images and the fake images. And so one way we can do that is just to subtract the two and take the average difference. So you're looking at here those Flickr Face HQ, the real ones, and subtracting the average StyleGAN. So when you take the difference between those two, you can get an idea of the differences. And the brightly colored white are big positive differences, and the black colors are big negative differences. So these are where the white and black are where the images really differ from one another. So just by looking at this image, we can tell what features that we need to focus on for our deepfake detection. So here we can tell that the hairline, the edges of the eyes, the corners of the mouth, the chin, the eyebrows, the nose, and the facial boundaries are all very important and something that we need to fake to our deepfake detection methods. And so we call these landmarks, facial landmarks sometimes. So we have noticed a general trend in detection methods. And the first thing that we have to do is find the face. It's important to note that finding the face is very simple for a human. In fact, I manually drag the bounding box around this person's face, just left to right, very, very simple. But for a computer, this is actually a pretty difficult task. And many years in computer visioning were spent trying to draw bounding boxes around faces. But it's come a long way, but sometimes the algorithms still struggle. But usually this is step one in trying to find these human deepfake detection pictures and images and videos. Once we do have that, we can start to look at the differences between the real and the fake. And we do that by extracting those facial landmarks and normalizing them. So again, those are like the eyes and the corners of the mouth. We're going to align and center them. And we do this so we can better compare the images to have more fair comparisons between them. Once we have that, we have something that we call masking and or adding noise to the images. And this is a way to make the machine learning detecting methods really work hard in a way. So to break this down, first we have the masking. And when I say the masking, those refer to the black boxes. In this case, they're going over the eyes and the mouth. Why we do this is sometimes that machine learning methods, they get, in a sense, sort of lazy in a sense. And so to speak, like for example, you could have an example of all images with blue eyes being classified as fake and all images with brown eyes being classified as real. However, we don't actually expect that to happen. And so if we actually just black out the eyes, we can make the machine learning methods find actual artifacts within the pictures to determine what's really making the differences between the real and the fake images. So that's masking. And then we also add noise. So you can tell here we added a blur to this face, but we can still tell that this is a human face. Sometimes that's not so apparent to the computers. And if we add this blurring, it can think it's something completely different. So by adding this to our training data, we can better inform the computer that it doesn't necessarily have to be a pristine picture of the face, but something like this is also applies to be a real person as well. So once we do all that pre-processing, usually what we do is send it to a pre-trained image detector. And we send it to a pre-trained one because people have spent millions of dollars training these features on millions, perhaps billions of different images and videos. And so since those are available to us, we usually just feed them through. Some of these pre-trained models that are available to us include ResNet and EfficientNet. So we have noticed a general trend, and once we have those pre-trained detectors, we'd have this final step of fine-tuning it. So what we do there is we send it through the detector, that pre-trained detector. It's not going to tell us exactly whether it's a real or deep fake. We have to change the last layer to tell us whether it is a real or deep fake. But once we do have that, we have our final step of evaluation. So then we are finally to look at different metrics such as accuracy, but other metrics as well, such as cost and time to make a prediction of whether something is real or fake. So how are we doing with DDP? Well, it's very interesting. So we have these different sets of data that we've talked about. And if we just take one of those pre-chain detectors, forget about any pre-transformation, and just send these images through, how do we do? So we trained the algorithm on the different data sets, and we tested it on different data sets, potentially. On the diagonal, you can see that we're doing extremely well, because that's when we're training and testing on the same distribution of data. In other words, this is when the model gets to see images that are like the testing set. So when the model sees similar images that it knows are deepfakes and has seen before, it can do extremely well as classifying them as deepfakes or not. But as you can see, if you go off the diagonal, that is when the model is looking at images it hasn't really seen before, different style of images, and you aren't doing much better than chance there. So the main thing that we're seeing with DDP is this problem of generalizability, but this is something that we're able to see right up front with using our pipeline. So some of our next steps include this generalizability, which includes model robustness. So we're really trying to find those artifacts with DDP that can make those methods that will work from one data set to the next. Other things that we're looking into include video-specific detectors, and then eventually we do want to improve our detectors via ensemble methods by taking different pieces from different methods and putting them together. So in summary, deepfake detection methods need better benchmarks, and these include accuracy, cost, and time. And we are doing just that with DDP in Juneberry, which includes data collection, data transformation, modeling, and evaluation. And we're making these benchmarks and putting out the results. So preliminary results confirm that generalizability is a problem, and we do expect to improve our models via DDP. Just as a final closing thought, this is a system where whenever we do better at making detection systems, the adversary can respond by using our improved detection results to make improved deepfakes. So this is a sort of game that we keep having to play, and having something like DDP allows us to have this reproducible results where we can quickly implement new methods. So thank you for your attention today, and I'm happy to take any questions.
Hello, I'm sitting here virtually with Shannon with a ton of questions around deepfakes. For those of you who are interested in asking questions as well, please make sure to jump on Discord and shoot some questions through the chat. So one of the things that I think is pretty interesting is that deepfakes are going to get bigger and bigger. What kind of guidance do you have for somebody like me who's maybe on a Zoom call or a video call, and I want to try to figure out if it's a real person or not, or if it's deepfake talking to me? Is there something I could do?
Good afternoon, John, and thanks for having me and all the questions that we're going to have. And so this one comes up a lot, and I would say fortunately right now we're at a point where when it comes to speaking live to someone, I still think a viewer who knows what to looking for the telltale signs should be able to tell if something is a deepfake or not. But for example, you can maybe guess that I am not a deepfake on the Zoom call, for instance. One of the reasons that you can maybe ask is, like, you can say, I can put my hand in front of my face. You won't see, hopefully, some very weird flickers. I can also move my face back and forth. And the reason why some of these doing this will help is that right now, some of the technology for live deepfakes are based around being as centered and still as possible in your screen. And that allows for some of the quickness, but at the expense of not being as precise and less fragmented than other deepfake technologies. So those are a couple things that you can do on a Zoom call.
Oh, that's cool. So just kind of sitting there and saying, hey, would you mind putting your hand in your face? Or maybe you could just kind of do repeat after me, kind of do a few quick tests, make sure that it's the real person.
I mean, it'll be entertaining at the very least. But yeah, those are actual things you can do.
Well, you mentioned that deepfakes are created for someone who's centered and looking forward. Can you talk a little bit about the state of deepfake creation? Now, how reliable are they? Are they robust, or is it pretty unreliable at this point?
I think compared to even a couple years ago, deepfake creation is at a pretty sophisticated state, and they're only going to get better in the next few years. And I wouldn't be too surprised in the next few years if the things I was telling you about, like such as the face, the hands, and moving the eyes, if that's no longer a quick and easy tell. So I think deepfakes are getting very sophisticated. The technology is improving very quickly. And so this makes it very crucial for us on the detection side to be able to keep up.
Wow. I mean, do deepfakes work on high resolution nowadays as well, or is it only like a low resolution kind of blurry zoom kind of a situation where if you squint, it looks good?
It's one of those where yes and no. For the live ones, again, I don't think it would be able to do as well, but with 4K resolution, for example, because those are very intensive computations that need to be done and processed. And right now, I have a hard time imagining that could be done live. But like when you see them in movies or something, I absolutely think they'll look phenomenal, but maybe not at the point where you could see them done in a live setting.
Oh, phenomenal. So do you think that deepfakes will get to a place where they're undetectable from real images at some point?
I think it's going to possibly be at that case. I don't think it's going to be instantaneous. And I think we on the defending side do have some tricks up our sleeves still, or avenues that we can pursue. But ultimately, I think we're always lagging behind the deepfake creators. So it's a real possibility, but at the same time, I haven't given up hope.
Oh, I see. Well, what do you think a deepfake future would look like when deepfakes are prevalent? And I could at some point I could pretend I'm Shannon on this call. Are there? I guess would we have to rely on things other than images or video, or any thoughts there?
Yes, and I think one important thing is, and sometimes people bring this up, is that deepfakes aren't necessarily the newest thing in the world. It's really just taking imitation forgery to a new level, and imitation and forgery has been around forever. So how do we get past that? So, well, there are some things that we can do that aren't necessarily AI, ML based, and I think this is right for a scenario that can be used with interdisciplinary collaboration, where on one hand, you do have some of the AI, ML to detect the simplest cases, but I also think that just having some certificates and authentications of different how to digitally sign our information, like we do in a lot of emails and such already. I think that's something that we can add to our videos as well, which I think will help a lot.
I see. Yeah, that's interesting. You mentioned like the people creating the deepfakes will always be ahead of the people that are trying to defend against them. So it seems like it's going to be like a game where we'll just always have to have active research and active development to try to understand how do we counter and work or detect deepfakes.
Yes, and I do think there may be a limiting end to this in the fact that I think it is a possibility that deepfakes are just going to be just as realistic as anything that you can see from a real photo or a video. And at that point, I think you're mostly relying on other features besides the image, such as metadata. But those are some things that we can always talk about. And but for the time being, there's a lot of different avenues that we can still explore, a lot of different features that are in the videos that we talked about a little bit in the video that can really point out what's a deepfake and what's not.
How about like adjacent areas? Is voice something that's already been conquered? So is voice something that's easily mimicable, or is that something that might come next, where not only do you see somebody that looks exactly like somebody else, but then it'll be indistinguishable whether they sound like someone else?
Yes, and I think voice can actually be some of the most malicious deepfakes out there, because I think they're a little bit harder, can be a little bit harder to verify. So absolutely, and then also text as well. You can start to imitate someone as their words. So you can do it all different formats, and yeah, so it's not just limited to video.
Yeah, I guess a question that came in and something that I'm kind of curious about is, what would it take for someone to deepfake me? Like, do they need to do like a 3D scan? Do they just need one picture? Or, God forbid, I'm on this video, and then if I turn my head, then there'll be enough information for them to create a deepfake for me. I was wondering, like, what does it actually take for someone to get enough information to make a version of my face?
So Kathy and Dom, who are two members on this team, actually did a real great work into this. And I think the answer to this is that, yeah, John, you've been on this webcast for a little bit now, and the answer is that you probably would be susceptible to a skilled deepfake artist.
Oh no, is there anything I could do to protect myself? So, I don't know, maybe always only showing one side of my face, or I guess there's nothing I could do about that, is there?
I think if you were somehow to consistently only show one side of your face, I guess, but then you would, unless you start to show the other side of your face somewhere else, then yes, it's certainly very hard. And I think about this a lot, especially since we're in the Zoom era. And everything's on video basically, and there's so much around to it. And yes, and there isn't so much right now that we can do. I think eventually we can start weaving in some watermarks into our videos and such, but that doesn't help all the video that's been out already.
I see. And one last question. There's someone that's sort of asking a question around, how do you figure out if you might have been, a deepfake? Are there tools to sort of search images and see if your face is out there somewhere?
I think at this moment, the best thing you can do is try a reverse image search. And honestly, that is one of the tried and true techniques to right now figure out if something is a deepfake. So right now that's your best, but maybe that's something that we should work on in the future, because that does sound really important.
Oh, thanks. Thanks, Shannon. Well, I appreciate you coming on and sharing your research about deepfakes and giving us a lot of practical advice on what we can do against the deepfake threat.
Yes, thank you. And yes, I think at least for now, hopefully we'll be okay, but who knows?
Sounds good. So with that, we'll move on to a short break. We're going to take a 15-minute break until 3:30, and we'll have a few small commercials and a few videos that we can show for those of you who stay on.
I am Dr. Xinghan Lao, Senior Cybersecurity Engineer and Principal Investigator of the AI Evaluation Methodology for Defensive Cyber Operator Tools project. Due to the ever-increasing quantity of cybersecurity data and the deficit of qualified cybersecurity personnel, many organizations within the Department of Defense and the defense industrial base have turned to AI-powered defensive cyber operator tools. It is critical for these organizations to understand the defensive capabilities of these tools to assess whether they are appropriate for defending their networks. Our project is dedicated to developing a methodology for evaluating AI-powered defensive tools in a black box method. Our methodology gives organizations a way to determine which cyber attacks a defensive tool can detect. Moreover, organizations can also use our methodology to estimate the sensitivity of a defensive tool to adversarial manipulation, such as data poisoning and obfuscation. Additionally, in a companion project to this work, we have created a test environment and tooling for the validation of the methodology we have created. If you are interested in collaborating with us on this research or transitioning it into practice, please get in touch with us.
Hello, I'm Andrew Mellinger, Principal Engineer in the AI Division of the Software Engineering Institute. Machine learning has become a crucial component to cybersecurity, logistics, threat detection, AI engineering, and other critical data-intensive operations. However, evaluating machine learning models to improve results can be a challenge. To facilitate machine learning experimentation, the SEI created Juneberry, a framework for automating the training, evaluation, and comparison of multiple machine learning models against multiple data sets. Juneberry's configuration files enable the user to employ machine learning terminology, not software development terminology, to reduce errors, improve reproducibility, ease integration, and adapt to the ever-evolving machine learning platforms. The user writes less code and Juneberry does the heavy lifting, taking the drudgery away from researchers. We've made Juneberry available to the community on GitHub. To learn more about Juneberry and how it can support your work on machine learning, please visit the SEI website.
Since 2004, the SEI has hosted FlowCon, a conference focused on using data to defend networks. From its earliest days as a small gathering of analysts to discuss network flow, to its current focus on situational awareness beyond the network, FlowCon has brought together researchers and practitioners to engage deeply with the latest tools, methods, and processes for using data to defend network systems. This year's conference will be held from the 9th to the 12th of January in Santa Fe, New Mexico. Our keynote speakers are Rear Admiral William Chase, Deputy Commander of Joint Force Headquarters, Department of Defense Information Network, who will share his expertise and experience coordinating defense of diverse and volatile information systems, and Mr. Jay Gasley, Acting Associate Director for Vulnerability Management for the Cyber and Infrastructure Security Agency, whose experience with managing and coordinating security and vulnerability management for large-scale systems provides something for all of our attendees to learn. In addition to a slate of research presentations from the Department of Defense Cybercrime Center, Cisco, the Mayo Clinic, Chevron, and more, we are offering open source information security tools training and workshops on emerging web technologies and cloud deployment security. I hope you will join us in Santa Fe this January 9th to 12th, and I look forward to meeting you in person at FlowCon 2023.
How do you hook a learner in 8 seconds when competing for the attention of the federal workforce? Transformative gamification engages your workforce by leveraging human psychology to enhance their experience. Our goal is to identify what motivating factors drive an individual to game in the first place, and determine how we can replicate that behavior to promote cyber readiness.
Our session will connect research in 3 DoD line-funded research projects featuring work in prominent cyber exercises and recent academic research. From the SKY program, Cyberkinetic Effects Integration, that blended real-world and cyber operations to provide simulation-based training that engaged both communities, to the Human AI Decision Evaluation System, HADES, which provided a test harness that allows the collection of human decision-making data on an arbitrarily large set of possible AI interfaces. Game-based techniques can improve the performance of human-facing systems and more. Join us in conversation on Day 2 of the 2022 SEI Research Review.
Welcome back. Next up, we're going to look at one of the hottest areas in AI and cyber, specifically, how can we use artificial intelligence to protect us? Speaking on that will be Dr. Xinghan Lao. Xinghan Lao is a senior cybersecurity engineer at SEI, having joined in 2018 after receiving his PhD from Carnegie Mellon and his bachelor's degrees from Berkeley. At the SEI, he has worked on AI defenses for cybersecurity, looking at how to test and evaluate those defenses. In his talk today, he'll cover AI evaluation methodologies for defensive cyber operator controls.
Hello, my name is Xinghan Lao. I am a senior cybersecurity engineer within the Cyber Risk and Resilience Directorate at the CERT division within Carnegie Mellon University's Software Engineering Institute. And I'm excited to share with you today our project, AI Evaluation Methodology for Defensive Cyber Operator Tools. So to set the stage a little bit, Organizations within the DoD and within the defense industrial base at large are turning to AI-powered defensive cyber operator tools to enhance their cybersecurity workforce. These organizations must assess whether these tools are in fact appropriate for defending their networks, and our project is aimed at addressing that by developing a methodology for evaluating these tools in a black box manner. So in terms of the agenda today, I'll speak a little bit to the motivation behind the work. I'll talk about the problem and our approach to solving it. I'll talk about the methodology that we created, and then I'll wrap up with some thoughts about future directions for this work. So starting at the beginning, why is it that organizations are turning to AI-powered defenses? So there is currently a significant shortage of qualified cybersecurity staff. So within the United States alone, there's a shortfall of about 700,000 cybersecurity staff. And for organizations within the DoD or within the defense industrial base, this presents a challenge because there are insufficient resources to hire enough people. And as a result, many organizations are feeling pushed towards using AI-powered defenses. So what is it that organizations are hoping to get from their defenses? Well, they're hoping that the AI can act as a significant force multiplier. For example, the AI may be able to address easy alerts and therefore free up human analysts to handle harder problems. Alternatively, AIs may be able to catch complex threats that may elude analyst detection. So, for example, the recent SolarWinds attacks that have been in the news. It's also worth noting that cyber attacks have now reached a stage where they are so rapid, where human response can be impractical. So, for example, the recent 2018 NotPetya attack took down an entire Ukrainian bank in about 45 seconds. This is so fast that human reaction is impractical. By the time your system administrator comes back from grabbing a cup of coffee, the damage may already be irreversible. Now, put yourself in the shoes of somebody who is responsible for purchasing or installing one of these defenses on an organization's network. What are the types of questions that you might ask before you go ahead and make this investment? Well, some of these questions might include, well, what kinds of cyber attacks can I actually expect the defense to protect against? What kind of cyber attacks are going to be beyond the detection capabilities of the defense? Does the installation of the defense itself create additional security vulnerabilities that an adversary may exploit that I should be aware of? And perhaps most prominently, how do I actually test the defensive capabilities of what I'm buying? So let me formalize the problem a little bit, and then I'll talk about our approach to solving this problem. So the testing and evaluation of AI defenses poses a challenge unlike those posed by traditional cybersecurity defenses. Organizations may need to evaluate these tools in a black box or gray box environment without direct access to the innards of the defense, particularly if you are responsible for purchasing a commercial product. Vendors are going to be very unlikely to share with you the secret sauce, right? The innards of the actual defense. In addition, AI defense designers are intending for their systems to learn from the network environment, and this necessitates the creation of a realistic testbed. Third, designers also intend for these defenses to learn and change over time. That is, in fact, a lot of the power of the AI. As a result, a singular evaluation is going to be insufficient because the defense itself is going to be evolving over a period of time. And finally, it's well known that AI defenses can be vulnerable to adversarial manipulations. And this can actually cause avenues an adversary can exploit directly that aren't present if you don't have an AI defense. So now in terms of our approach, actually creating a testing and evaluation methodology. So based on those 4 challenges that we identified, our methodological approach must do 4 different things. First, we need to create a realistic network environment where our AI defense can be deployed. Second, we need to ensure that network environment is populated with sufficiently realistic background traffic that will allow the AI to learn what is normal for that particular network. Third, we need to test the AI defense performance against realistic cyber attacks. And finally, we need to test that performance when the AI is actually exposed to adversarial manipulation. So now let's talk about the methodology itself. So we'll first start with a network environment. So this is the network environment that we're currently using. This is intended to be fairly simplistic, to cover sort of the basics of a network environment, but this presents an opportunity for us in the future to be able to expand upon this work and make it more realistic in terms of a modern network. So at the bottom of the slide there in the green is the user network. So these are all the individual employees within this organization. They all have their own workstation that they're using, and that's obviously connected to the company network. In blue in the left, there is a server network, so a variety of services that are typically offered to a user. This includes things that Windows will require, such as a domain controller, and will also involve things like a file server that will be common to different architectures in a network. On the right, there is the demilitarized zone, the DMZ, which contains things like a web server. It contains internal email server for the organization, as well as some shared resources. In the top right is the world simulation, right? This is the outside view into the organization. So this includes the ability to send and receive external email from parties who aren't part of the organization. It also includes the machines from where our cyber attack tests will be launched from, and also includes a variety of web traffic simulation, including actual web access. All of this traffic within the network is centralized around a single router, and the AI devices that we will be examining are going to be attached to that router. So what traffic are we actually putting on this realistic network environment? So in order to talk about traffic, we first have to talk about the users that will be generating the traffic. So we have created 99 different employees split across 5 different divisions within our company. And each of these employees has a unique behavior. This unique behavior is based off of things like the work schedule that the particular employee prefers. It depends upon the role that the employee plays within the organization in terms of the work tasks that they'll perform. So for example, you'll find somebody in HR will do HR type tasks. They'll do performance reviews. They will go out and try to interview. And you'll also see that, for example, somebody like a CEO will perform more executive style tasks. In addition, we've also assigned each of our users a set of personal hobbies because, of course, modern networks are not just strictly for business. They often include some provision for reasonable personal use of the network. So our users will go out and access sites that are reasonable for the hobbies that they are interested in, whether that's gardening, whether that's gaming, or whether that's just browsing the news. It's important to note that we also set the privileges and accesses for each user according to the role that they play within our organization. So you won't find that some random accountant will having system administrator access to the network. That's going to be reserved for the system administrator because that makes sense for the job that they're performing within the company. In order to simulate all of this traffic, or in order to generate all of this traffic from this simulated user behavior, we are using a piece of software called SEI Ghosts, which stands for General Hosts. So this piece of software allows us to take all of these behaviors that we are describing and turn them into actual actions that the employees will take on their machines, and as a result, generate traffic. This traffic results from the simulated behavior. It's important to note that we are not simulating the traffic directly because that type of approach can lead to a great deal of artifacts or a great deal of bias in terms of what we create. So that's our network environment. What types of tests are we actually performing as part of our methodology? Well, of course, what you actually care about, if you're the person who is responsible for actually determining if this defense is effective on your network, is whether or not it detects particular cyber attacks that you care about. So what does a typical cyber attack look like? So here we have a 10-stage process. We start with, on the very left here, a pre-attack preparation step. So that might include an attacker looking around for credentials or scouting out various employees on something like LinkedIn to understand what it is that the company has that they're attacking. Once the adversary, the attacker, has identified a target, they'll attempt to gain initial access. So this might be, for example, sending a phishing email to somebody within the company based off of information that was identified in step 0. Once a user has inadvertently clicked on this link, this allows the attacker to create a threshold in step 2, and that then allows them to set up their command and control, or C2 network. Once they're on the network and they have their command and control established, this then allows the attacker to take a bunch of steps to find what they're interested in on the company's network. So this might include a series of privilege escalation steps, finding appropriate credentials, discovering what is actually on the network, performing lateral movement to get on the right machines, And finally, to identify the particular data that they care about and to collect that they will then exfiltrate in the final step, thereby completing the cyber attack. In terms of the cyber attacks, we've created many different attacks, and we've decided to map them to the MITRE attack framework, which is a common cybersecurity attack framework. And this is largely to allow us to present our findings and our testing in terms of what is understood by the broader community. So you'll see on the left, these are the various categories we've binned the MITRE attack framework into. There are some things, there are 57 of them in the gray, that are not going to be detectable by an AI. So this, for example, might include looking at external social media sites or trying to look for various credentials on the dark web that might not be that might not touch the company's network at all and therefore would not be detectable by any AI. There are currently 70 of these elements of the MITRE attack framework that we are currently using. And of course, that means that we both have the ability to execute the attack using something called MITRE Caldera, which is a piece of software that we are utilizing. It is also important that we ensure that our network is vulnerable to these attacks, of course. There is another category there in yellow where Caldera is actually able to support these attacks, but we are not actually vulnerable in terms of the network that we've created. There are a series of 30 attacks that the network is vulnerable to but are currently not part of Caldera that we may look to add as this is ongoing work. There are some elements that we do not believe we'll be able to actually have available on our network because our network simply doesn't support them. And there are some elements that we've identified as potential obfuscations, which I'll talk about in a little bit. And it's important to note here, the reason we break up into these various categories is that, of course, not all of the attacks within the MITRE attack framework are actually going to be detectable by the types of AI defenses we're considering. So we need to understand what is actually practical for an AI to detect so that we can focus our testing on that. Now, of course, I've talked about having these cyber attacks as a baseline evaluation of our AI defense. But as I previously noted, there is this need for continual evaluation. Of course, the AI defense designers have deliberately intended for the defenses to constantly learn from the traffic that they're observing. And as a result, the decisions that the defense will make will change over time. Evaluating a defense at a single point in time is therefore insufficient. And our methodology calls for a continual evaluation of the defenses to gauge how their defensive capabilities may actually change over time. And note that one of the challenges here is that we need to create the tooling to actually support this type of continual evaluation. Now, I mentioned at the outset that one of the challenges in testing an AI is that it is vulnerable to adversarial manipulation. So there are two categories here. The first one is obfuscation. So what does it mean? So obfuscation simply refers to the fact that an adversary may attempt to evade detection by obfuscating their attacks. This may include changing tactics, for example, by using a different tool to perform the same tactic to avoid behavioral characterization. They may also try to do something like using a different lateral movement path to gain access to the resource that they actually care about, right? The collection of data that they actually care to exfiltrate. The adversary may also try to modify details of their attack. So, for example, there may be some steps where they can interchange the order of events. They may also be able to change the protocols that are used. So instead of sending something out over HTTP, they may use HTTPS. They may instead use something like DNS, and they may vary the protocols so that based on what they think the AI may actually detect. Of course, there's the classic going low and slow, right? Decreasing the rate of tasks. And there's also the thought that you might want to change the time of day that you're actually executing some of these steps. So it may be a lot less obvious if you execute something during the course of the business day as opposed to at 3 a.m. in the morning. And of course, an adversary may also seek to use encryption, which is going to make it much more difficult for an AI to really understand what is passing on the network. There are some considerations here for the adversary, though, as they're looking at obfuscation. First, the adversary must still accomplish their original objective. That is, their attack must still succeed. It does no good to obfuscate to such an extent that the original objective is not met. Second, the attack itself may take longer to succeed due to various rate limitations or because a very circuitous path has to be taken. It's worth noting that there are a limited amount of resources for testing, so things like bandwidth, computing resources, and testing windows are also a concern. The second type of adversarial manipulation is data poisoning. And this is something that is very specific to machine learning and AI systems. In data poisoning, an adversary causes the system to learn the wrong thing. So, for example, an adversary might provide valid and seemingly benign traffic to adjust to the decision boundary of the AI. By feeding in specific poisoned traffic that is valid, the adversary can cause the AI to think that future attack traffic actually looks benign. So as a practical example, suppose that the AI is attentive to the volume of outbound traffic that is sent from a particular internal host. Data poisoning in this case may consist of sending out a high volume of benign traffic from that host. So for example, sending out an email with a lot of large attachments, sending out a lot of uploaded web traffic. And by doing that poisoning, it may now make it so that when the adversary attempts to exfiltrate a high volume of data from that particular host, it is more likely to succeed than before the poisoning. Of course, as with obfuscation, there are some considerations here. The addition of poison traffic itself may set off alarms, which would obviously defeat the point, so an adversary must take care to avoid detection. Additionally, an adversary needs to have some idea of what a model is using in order to gauge what poisoning may actually be effective. It does no good to poison along a dimension that the AI does not actually consider. In terms of the methodology, we also have a separate project where within the current project, we are actually trying to develop the underlying network and the underlying tools to actually be able to carry out the simulation. We are also looking to, in future work, carry out actual validation of this methodology. So for example, to carry out baseline attacks, attacks with obfuscations, and attacks with data poisoning against real systems, with the goal being to show that the methodology is effective, to measure the fragility of systems to various different types of attacks, to determine what an assessment might reveal, and to determine how much effort and length of time might actually be needed to perform such an assessment. Of course, the goal here is to also identify limits to our methodology and also to develop the requisite tools to support practical testing and validation of the methodology that we've described here. All right, so to wrap up here, the key takeaway message is that testing is key for our AI defenses. The effective use of AI-powered defensive operator tools requires our ability to actually evaluate their capabilities. And testing of these AI defenses is actually quite different from the testing of traditional cybersecurity devices. So an organization needs to be able to test these AI defenses in a realistic network environment with realistic traffic. Additionally, because the designers of these defenses have intended for them to be able to change their behavior over time, we need to be able to support continual evaluation. And of course, defenses are actually, these AI defenses are subject to adversarial manipulation through things like obfuscation and data poisoning. Finally, it's worth noting that our methodology helps to address some of these concerns by testing the capability of AI defenses against actual cyber attacks, and therefore provides organizations with insight into the defensive capability that they provide. And the cyber attacks that we're considering are actually mapped against a common framework, which is the MITRE ATT&CK framework. In terms of where we hope to take this project in the future, we hope to be able to also consider different types of AI defenses. This might include, for example, endpoint defenses or the cloud-based defenses that are becoming increasingly common. We hope to also expand our testbed infrastructure to include non-enterprise networks. And we hope to also be able to develop a similar methodology that allows us to employ replayed traffic, that is, traffic that is collected from a specific network of interest and is then replayed with attacks added into it. It's worth noting that we are actively seeking collaborators and transition partners for this current work that we're doing and also for this upcoming future work, and please contact us if you're interested. So with that, I will leave you with the pictures of the lovely team that was involved in this project, and thank you for your attention.
Hello, I'm here sitting virtually with Dr. Xinghan Liao, and we have a chance to ask some questions about his work on AI evaluation methodologies for defensive cyber operator tools. For those of you who'd like to jump in and ask a question, feel free to type it out on the YouTube chat, or you can also ask the question on Discord and then it'll get to us. So I guess the first question I have for you, Xinghan, is where do you see the future of testing AI devices to go?
Sure. So I think the future here is going to go in a couple of directions. So first, I think we're going to move more and more towards a continuous evaluation model. So a lot of traditional cybersecurity defensive tools are kind of very rule-based and very strict in what they allow. So you can just basically try them once and make sure you do your set of validation tests and make sure that you're happy with the results. And that's good enough, right? But the upside and also the downside of AI is that it is inherently designed to learn from the network traffic that's being generated on a particular network. And because it's supposed to adapt, it means that a single point of evaluation is insufficient. So I imagine that we'll move towards more and more frequent testing, and then eventually we'll get to some sort of continuous model where you'll have some sort of system or some sort of team that's basically continually checking to make sure that your AI is actually performing within the bounds that you're expecting, and that you're actually getting the results from a product or a defensive tool that you hope to get.
Interesting. As a follow-up to that, I know that testing tends to be challenging because there's so many things you can consider to test. And then testing is also something that could require a lot of resources to do correctly. I guess imagine like I'm somebody who needs to figure out how to test these devices. Any advice on how do I prioritize or what to look at or how to build out my testing approach?
Sure. Yeah. So testing can take a lot of resources, and one of the things that certainly should be prioritized here, especially with an AI, is in understanding whether or not it's going to maintain its level of performance over a period of time. And that's one of the things that we've tried to get at with our methodology, right? To really understand that if my AI is working properly and it catches something today, is that still going to continue to catch that in a week, in a month, and in a year, right? And then also to understand, especially since here the AI is actually the defensive cyber tool, to understand that if you have adversarial manipulation in some way, right, through obfuscation or through data poisoning, is that actually going to affect the performance of your AI, right? What amount of defensive capability do you still have if your adversary is very clever and knows you're running an AI, is actually trying to confuse it directly? It's really important to understand whether, at what level of sort of adversarial influence you still have unchanged performance, at what level you have some sort of degraded performance, and at what level your AI stops working completely. And that's certainly something that you really need to understand, because otherwise you're going to deploy something and something unexpected will happen sometime down the road, and you may not even be aware of it, and that would be potentially have very negative ramifications for somebody using a product like this.
Interesting. Yeah, and one thing that I think of is you mentioned that there could be a vulnerability or something could go wrong. Like, what do you think about that time span between catching something's gone wrong to redeploying, and how do you optimize for that, or how do you reduce that exposure?
Sure. Yeah, and certainly the continuous evaluation side of things, or the more frequent evaluation, at least, that I alluded to earlier, I imagine that has an impact, right? If you're able to test more frequently and identify that you have a problem sooner, and ideally you are the one as the defender who realizes you have a problem, you're not made aware of that by some adversary doing something nasty on your network. If that is the case, then you can at least deploy a fix sooner, right? But there's also a question of, well, even if you have a defensive tool that misbehaves in some way and you want to deploy a fix, it's a question of, well, is that just merely a matter of training a new model in order to accommodate whatever it is that I've somehow left out of my original training set? Or it could be a more systematic problem, right? That if you have just looked at a particular model and that has does however well it does, but the underlying problem is actually that the way the model is integrated into the system is somehow ineffective, right? Perhaps it does not have enough safeguards where the ML is allowed to just kind of go totally haywire if it learns completely the wrong thing. That's something that you would really like to be able to, ideally identify during the design phase, and how you accommodate that if it makes it into a live product. That's a tricky question. I don't know that I have the answer to that, nor do I know that anybody else really has the answer to that. It's still an open question.
Yeah, thanks. And I also sometimes think about the difference between testing the system versus testing the model. So what do you think about the major advantages of testing an entire system as opposed to just testing the machine learning model?
Sure. So testing the model is something that a lot of, especially machine learning folks, gravitate towards because it has a lot of simplicity to it. So first, you're just testing the model side of things. So it's very clean. You just put in whatever input data you have, whatever training data and test data that you have that you're interested in. But what you lose is the fact that this machine learning needs to be performing in the context of a larger system, right? And that larger system will have various sensors all throughout it. It has various pre-processing pipelines. Eventually it will, of course, see a machine learning model. But then once you look at the output of that model, you might have various post-processing steps, and you may even have some sort of decisions that are made on the basis of whatever your model has actually said. And by evaluating the system, you're actually understanding whether or not the system is going to work as a whole when it is deployed in its environment. Whereas if you just look at the model and you say, well, the model works great, but that might be conditioned on the fact that you actually have really good incoming training data. And if your sensors are the actual problematic part of your entire system, you're not going to detect that when you're just testing your model.
Yeah, that makes sense. I have to think about that a little bit too, because there's so many different places you can test, like the interaction between the sensors and the model and the data in the model. So it also makes the problem a lot harder.
Yeah, absolutely.
And last, and then I guess we're out of time. I had one more question, but maybe I'll ask you that offline. Well, with that, I wanted to thank you, Xing'an, for coming and sharing your research with us and kind of illuminating how important it is for us to test our AI for evaluating our defenses.
Absolutely, my pleasure.
Thank you. So with that concludes our session today on our accelerated delivery and adoption of AI. We've heard from a number of talks. We've heard from Dr. Stryline on how the DoD will accelerate AI for the DoD decision advantage, and how the DoD, labs, industry, and industry partners will work together to make this possible. We heard Dr. Heim talk about uncertainty in ML and how it remains an important challenge for AI engineering to make things reliable and robust. Dr. McMillan talked about bringing ML to the edge and the opportunities for building custom algorithms for tiny situations. Dr. Lewis and our team talked about the mismatches in the organization and how they create both challenges and opportunities for the success for ML. Dr. Gallagher talked about deepfakes, how we can find them, and some practical advice for us as users on how to avoid exposure to them. And just now, Dr. Lau talked about how AI can be used for security and how important it is to test our AI device or AI to make sure that things are still secure. We're going to resume our research review tomorrow at noon Eastern with a focus on highly secure cloud-native architecture and enhancing engineering rigor. We're going to have some talks on gamification for threats and cyber readiness, model-based engineering, DevSecOps, and safety for cyber physical systems. Thank you all for joining today, and we look forward to staying connected with you. Thank you.